Good. Today will be our last course. Normally there is also course week next week, I know, but I won't be in Belgium, so a bit difficult to teach. And if all goes well, we should also be able to go through the content. If for any reason we won't make it, then I will post a recording afterwards to make up for that, but normally it should be okay. Also, I will later tonight probably also post an update with regards to the closing of the leaderboard of the very first assignment, so that the hidden part of the test set will be released. Very likely the closing date for the leaderboard will be next Monday, so during the time when we normally have course, Monday evening somewhere, that will be the final time by which you can submit your final attempts, let's say. So you still have the weekend to do that, but I know that most groups already have made a lot of submissions, so normally you should be pretty much done with that assignment anyway. Before we get started, so today we talk about graph learning and graph analytics. A bit of in the news. Last week we talked a bit about the transformer architecture and those attention scores. This is a person that has been following along with, there is a tutorial online from, I think it's from Sebastian Raschka, about implementing an LLM, a GPT-2, basically completely from scratch in code. This person has been following on with that, posting, blogging about their thoughts and results that they get. And they have meanwhile arrived at part 13, which is exactly about the implementation of these attention scores, and where you can have a look at if you would also like to follow along and maybe at some point code like your GPT from scratch to get like a deeper understanding or to kind of refresh a bit how all of these attention scores work. This is a publication which is quite new. I haven't had the time yet to really dig into it in depth myself, but it looks pretty impressive. Let's see. It's better to show it in motion. Not this one. So this is about continuous start machines. The idea is that they try to bring a standard neural network architecture a bit closer to, again, oops, that's not visible for you guys, sorry. Where am I? Not here. Come on. Also not there. That's weird. Okay. Ah, yes, there we are. Yeah, so trying to bring a standard neural network architecture closer to some aspects, or again, a little bit more inspired by how the human brain works. And this is something where they try to get inspiration from the way how our neurons in our brain, when they fire, when they use certain timings to do that, and where there is also some synchronization that goes on between the activations of neurons, let's say, being passed or being sped out, rather than if you compare it to like a traditional architecture where the activations of every layer just appear there at once before they're being sent as inputs to the next layer. This is a paper that kind of challenges this a little bit. Looks pretty cool. They have like a small example going on where based here they kind of show how you can teach a network to find its way from one position in a maze to another position in a maze, and how it's kind of visualizing the pathways as it goes forward. It's a simple idea, but it seems to be relatively promising. Thought that was cool, so definitely have a look at this if you want to read more about this. Might become the next big thing, might also not. A couple of years ago we had like another attempt at revamping neural networks in the form of KAN networks that also really didn't go anywhere, even though at some point the hype for that was pretty high as well. But check it out. In any case, it's a pretty cool visual. Also, a bit related to what we have already discussed previously, when we spoke about dimensionality reduction, we had seen both t-SNE and especially UMAP as kind of the two most utilized techniques, especially when you deal with high dimensional data. At that point, I also told you that UMAP in particular is very popular in bioengineering to perform layout of cell atlases and things like that. And here there is a new paper from that same background that presents an alternative dimensionality reduction technique, which is more tree-inspired, so they call it bonsai. They claim that both PCA and UMAP and t-SNE and so on, that they have some issues. They are stochastic and they distort the underlying data structure. And they claim that their attempt, at least for cell mapping, works better because it has special ways how it deals with measurement noise and so on. There is nothing blocking this from not being utilized with other sorts of high-dimensional data. They have a GitHub repository available, so basically it's going to be fun to see how well that how that this technique stacks up against UMAP if you would also apply it on other high-dimensional data structures. Like the typical use case for UMAP and t-SNE is let's take images just as they are in raw format and let's place them or embed them in this two-dimensional map. We'll see, or let's run Bonsai on this and we'll see what happens if we do that. So also very new. Let's see where this goes and whether this can dethrone the current UMAP algorithm. This is, again, a diffusion model, but a little bit special, applied on garments. So this is also something that has been recently released. Not this one, but this one. And it's about garment sewing pattern generation, again, with diffusion transformers. Why do you need a transformer? Because they need to sequentially generate like points in this plane where you need to basically cut the garment. So it's good that you have some sequential model there. And then every step applies some sort of diffusion, like we saw commonly in other use cases as well, to basically then fit in the pattern that you are generating at every step. Our good friend Clip is there as well to basically match what's being generated with a textual prompt. And then they show some examples, and they have a whole demonstration video up here where they show their results of, can skip forward a little bit. But you get pretty, well, I don't know much about fashion, obviously, but you get relatively nice looking or convincing looking sewing patterns, again, starting with random lines, random noise, and diffusing from there the end result. So pretty good, generates pretty fast as well. So also the AI in the fashion industry is something that's of course rapidly growing as well. Next up, we have, also this is a little bit of a detail, let's say, and you can dig into the sources that are listed there if you would be interested in this, but like people are continuing to work towards applying reinforcement learning in the context of post-training of LLMs. And we saw that last time, like you basically have two generations of a prompt and you ask a user to indicate what their preferences are, and that's what you utilize to perform further fine-tuning of your LLM after the supervised fine-tuning step. There are more and more papers that claim or that are trying to reduce the number of examples that you need to perform this reinforcement learning step with, because the more examples that you need, the more users that you need to ask feedback from. And now they are really pushing this to extreme situations where some papers are even claiming that if you find one very high quality example, that a single example can be sufficient to basically perform the fine-tuning of your existing LLM. And the magic thing here, or the interesting thing is that they say, well, contrary to with supervised fine-tuning, where if you would use like a normal supervised training loop and you will only have one example, what's going to happen with any sort of network, obviously it's going to overfit on that single example. And they claim that this is not what's happening here. They say, well, because this is now detached from the immediate updates of weight gradients, but because it's rolled in this reinforcement learning step, and every time you're asking the network to basically regenerate its thoughts or its prompts based on that single example, they at least claim that you do not have the same kind of overfitting happening if you do this or if you do these sorts of things in the reinforcement learning post-training, rather than if you would do something like this in the training step itself, because then obviously with a single example, your model would end up horribly overfitting on that single example. There are a couple of various papers that have recently released. You can check out the links to know more, but this is also going in pretty interesting directions as well. And then finally, summer is coming up. If some of you would be Lego builders or you like to play with Lego, there is a research group that has taken, again, a language model, something that looks like GPT, and they have adjusted it basically to generate models, let's say. Lego structures, they're not like huge models with 10,000 pieces yet, they're all still relatively small. So small structures that they can generate with this thing, but the interesting thing is that they have been able to construct this model in such a way that all the structures do not just look interesting, but that you can also actually physically build them step by step, and that they, at the end they are stable. They don't topple over or they don't fall over, so they are like believable structures, real-life structures, convincing structures, things that you could actually build and have working if you build them. So they use some interesting tricks to do that there as well. In the end of the day, you need to have your model or build in some knowledge or a world knowledge in that model in terms of how do physical objects work, what causes something to fall over, what's the sequence here in which that the user places these blocks. You can't just start with a block in the middle and then put something around it in the incorrect order. I mean, that physically just doesn't work. So they have been able to do this. But again, all the objects are still relatively simplistic, but who knows? At least it's also inspiring for like making models more engineering aware, let's say, or making things that are not just look cool, but are also physically possible as well. So okay, with that being said, we can take a little bit of a look at our graph analytics section. And here too, it's going to be quite of a similar story as back when we spoke about images and when we spoke about text. We always had like the initial attempts, which were heavily featureization driven. Basically, how can we manually come up with, again, good representations that we can then give to our favorite supervised learner, versus after deep learning happened, people looking more towards, how can we just take this existing thing as it is? In this case, that will be graphs. Previously, it was text, and just dump it in a network and have it end-to-end learn certain representations for the things that we need, and then for our downstream task that we wanted to predict. And in the case of graphs, very often, if you think about nodes in a graph or in a social network, for instance, we'll see a couple of examples immediately. But for instance, you would like to, on a node level, very often make your predictions. You have, if you're a telco provider, you know which of your customers have been calling one another and how often. Then you observe, well, some of these customers, they have already left me in the past. They are still receiving calls, and if my customers call that person, I can still see that they are calling them, for sure. I can't see their calls anymore because they are at another company, fine. But now, given this historical observation of you have already left me, can I then try for the other customers that I still have in this call detail record graph, the graph of calls that have been made, who is likely to leave me in the future, for instance. Also, fraud cases also quite commonly make use of graph-based structures, but you have many others as well. If you think about more social networks, then maybe there your predictions are more at the link level or the edge level. You would like to predict whether these two people are going to become friends in the future, for instance. So there is going to be an edge that appears over time, or maybe two people break up their relationship and the edge will disappear. So maybe you can think there of edge-level prediction tasks. So very often, if we look at a graph, the instances that we will want to predict something for, in the majority of cases, they will be node level. So for every node, we have a label, yes, no, in the case of binary classification, and that's what we want to make our prediction for. In some cases, that will be edge level, and edge is going to disappear or appear or something like that. In very uncommon cases, sometimes the instances themselves are all complete graphs on their own. That can also happen. If you look at molecular analysis, for instance, if you take like a molecule or a protein, that's basically a little graph that you can build out of that, and you have a network predict, well, I have here 10 suggestions for how I can build a molecule in my perfume factory. Can I predict which one of these will smell like roses and which one of these will not? An extremely difficult task, by the way. Molecules can look very similar to one another and might smell completely different. So very difficult task to do. But that's a task where if you work at the molecule level, that every instance is a little graph on its own. And then the label applies on the whole graph rather than all of the nodes or all of the edges. Most commonly is that we work at the node level. So, okay, a couple of further examples. If you think of web pages and hyperlinks, the pages are the nodes, the links are the edges or the arrows, say, between them. If you would follow email traffic, like the well-known Enron case, fraudulent case, a company that committed accounting fraud and so on in the US, people analyzed the email traffic of the employees in that company to kind of see how that notion of that fraud was spreading and where collusions were happening and so on. So that's a very well-known case. Or you can try to use it for HR analytics to see how people are working together and so on. Research papers, they cite each other. You can also make a graph out of that. If you're a financial provider, say you're a bank, right, then you have an enormous data set of transactions, financial transactions, money that people receive and send to one another. That's also immediately a graph that you can utilize to perform analytics on. And make no mistake, every bank today in Belgium is doing that, right? Even although they care about your privacy and they will anonymize the data in some way, but they're all doing that at this moment. Telephone calls, I had already mentioned, and of course social networks may be the thing that everybody thinks about at first. So you think about social networks, yeah, those are graphs, so Facebook, LinkedIn, Twitter, X, who knows what. People follow each other, they befriend each other, they send messages to each other, so obviously that's also something that makes for a good graph. What do you utilize it for? Well, marketing analytics, see which of my customers is going to leave me based on those that have already left, and you think that are word of mouth effect, so churn detection. Spread of illness, of course, we have all had, or we went through COVID. Graphs are a quite common representation format for meetings between people, and then one guy gets sick, and we want to then predict how the illness propagates throughout the network. Fraud analytics is common. If you take that a step further, terrorism detection, also there links between actors are a very important thing to have. Palantir Technologies in the US, that's their whole use case basically, is linking everything together and allowing analysts to explore this, and so on and so on. Of course, recommendations, also very an interesting or an obvious use case. People like you, they have also frequently bought these products as well. So if you keep track of who bought what, you can kind of cluster on that graph and make suggestions based on that. So this is the example of email flows. So every node here is a person, and then it got a color based on the department that they are working in, and then a link was simply placed if these two people at any point during the observation frame had sent an email to one another. You will also note here that the edges are not directional, they're just lines. A little bit more about that in a second. But then you get something like this. Interestingly here, people like looking at graphs, and also it's immediately quite revealing what's happening here. You have three main departments, the green guys, the red ones, and the blue ones. And then you have these yellow nodes that are all over the place, but these are consultants, so it's normal that they pop up all over the place. And then you have also nodes that are all over the place, but they are very infrequently contacted. So they end up lying at the edges of the network, the gray ones, and those are really external experts that are being contacted in a one-off by one person to give some advice or to give some feedback. Now, here there is nothing really predictive going on yet. We are not giving no labels to these nodes and asking, well, what are they going to do next month from now or whatever. This is basically you construct your graph, and then the main bulk of the work in this case is being done by the layout algorithm, right? The algorithm that decides where should I position all of these nodes in this 2D plane that I have here, right? Of course, what most positioning algorithms will try to do is make your graph look where the densely connected nodes end up being close at one another, and then the not so densely connected ones, they can be a bit further away. And you have different algorithms that exist. That's a research field on its own. But very often, if you apply a solid layout technique, then immediately also just visually, you can kind of already see like clusters or communities, say, that appear in your graph. This is another example, the famous case of the Panama Papers, already from quite many years ago, but the Paradise Papers, the Panama Papers, both were cases where journalists got hold of a lot of financial transactions that companies, politicians, and so on, CEOs had done in terms of, as the name suggests, in the case of Panama, in terms of institutions in Panama, which is a very often used place if you want to avoid paying taxes and things like that. So they got hold of a complete data set. They spent a lot of time going through those transactions and documents and linking everything together. And from there, you get a graph that you can start digging in. Again, not really a predictive case. They then mainly used filtering tools like Linkurious and others to drill down, zoom in, query the graph, lay it out in a certain way, and then go manually hunting for interesting stuff in there. But very often, in a lot of cases where you see graphs, that's still what people end up doing. So even then, they will call it, we did graph analytics. But the analytics is basically we use a layout technique, we filter the graph, we have a look at it, we explore it, and we see the interesting things that pop up in there. So that's also a very commonly known case. This is another one just to kind of indicate that also in fraud, graphs are frequently being utilized. This is a network of credit cards, which are the yellow nodes, and merchants are the blue nodes, and this is just like a fragment that's taken. Here we do have labels, and here credit cards are being utilized in stores, right? So you already have two node types here. And the label here is not being carried by the node, but it's being carried by the transaction, by the edges. Because of course, if you have your credit card, you're buying stuff with that, those are all legitimate transactions. At some point, your card gets stolen. From then, the edges become red rather than green, because someone is using your card to buy stuff in an illegitimate manner. Here, just to show like why is it useful to build a graph out of this? I mean, what's the pattern that you can extract from here? Well, very often what you see is that once a credit card gets stolen, those cards tend to be utilized in a common set of merchants. Doesn't mean that that merchant is fraudulent. Doesn't mean that that always happens. Doesn't mean that those merchants never have normal transactions, but just on average speaking, stolen credit cards do tend to be utilized more in certain places. And if you ask people, what kind of merchants do you think, the one with the red box, that these cards frequently get utilized in once they get stolen? Sometimes the answer is jewelry. But of course, with jewelry, you need to go to a physical shop And if you go to Antwerp, the people who run those shops, they are pretty good at looking at you and figuring out that you're not up to a lot of good stuff. Now, of course, the answer is gift cards on the one hand. You just buy a whole dump of Amazon gift cards because you can try to resell those in some way. And also, for some reason, Apple hardware is also pretty popular because it also retains a lot of its resale value. You can go to some pawn shop or a black market or some guy that you know, and you can still get like a fair price than if you'd have bought like another machine, which is way harder to sell on the second-hand market. So that, again, as an example of how stuff can stay or can appear if you represent it as a graph. This is about identity theft. What you see here, obviously, you're looking for those cases where a person has their normal list of contacts that they communicate with, that they call with, and at some point their SIM card gets stolen or there is a sort of identity theft that occurs, and suddenly that person, or from then onwards, suddenly a whole bunch of new contacts appears in that graph that's suddenly being contacted. It's also a pattern that hopefully we can pick up on. This is all still visual. It's like a couple of examples. At the end of the day, what we would like to do is have some sort of model in a data-driven way, being able to look at this topology and hunt for these kind of patterns that are correlated with the target that we want to predict by itself, right? This is so far just us looking at examples or someone looking at examples and going, ah, yeah, I see something here. You can even try to extract a rule based on that, right? That would be a first step, let's say. But of course, our goal is to use this data structure directly in an end-to-end style of model. This is the churn example. The red cases here, so this is a group of friends, a fragment again of people that have been calling one another, and the red cases here are those customers that have already canceled their contract. And then the idea is, can we model this in some way where, because of word of mouth effects or because of promotions that these red guys are getting at their new provider, who of my existing customers is likely to churn then in the next month? And already here, that propagation effect that's also being used to model spread of illness, it's the same thing that you can apply here. If you look at churn as some kind of disease that these people got or these customers got, well, who is most at risk of being influenced? It's probably the ones that have a lot of red friends, rather the ones that are still very far away from them. Is there a way how we can put some quantitative measure on top of that? We'll see those as well. And this is the example of a case study to spread how a disease outbreak spreads through a social network. So also from a couple of years ago already, but like I said, during COVID, we saw exactly the same things. Like you start geographically, but you make a graph out of that, and you also use that to monitor the occurrence of positive COVID cases over time. So similar techniques, modeling of spread, modeling of propagation, modeling as it's called, very common as well. Now, annoying for us is that if you just start with a graph, it's again the same case as with text and images. It is not yet a feature table. So it is again semi-structured. It is structured because yes, we do have nodes and there are connections, but we again do not have a direct feature vector representation. And in a case where we would like to predict on the level of nodes, then of course the idea is again here, well, how can I now extract or enrich my representation that I have for all of these nodes, for all of my customers, using that graph topology? And probably I already have a lot of static features available to me. If you look at this graph, for example, I probably know the age of all of these customers, and I know which type of mobile phone that they have and how often that they are on the internet on their phone, and are they 5G users or 4G users, and you probably know where they live and so on and so on. Question is, how can I then enrich that feature vector by maybe taking some stuff that I can extract from the graph over here? So again, that will be our goal. Now, what we would also have to think about is, we saw a couple of examples, but even in the case of that telco example from just now, for instance, yeah, someone has to decide how we are going to construct this graph in the first place. And for some reason, or in some use cases, this is more apparent. If you think about financial transactions, okay, then people send money to each other, so you have an edge every time there is money being sent. In the case of a call detail record graph, okay, if people call each other, there is a connection between them. Yeah, but they also send text messages to each other. So what does this then become? Does this become two types of edges that we would then need? Do we give these things or these edges a weight or not? Do we make them directional or unidirectional? So there are lots of trade-offs that you can make in terms of making your graph very simple in setup and probably nice and dense, versus making it very rich in terms of representation, but probably also a little bit more sparse. So that's not always an easy thing to decide upon. It requires experimentation. So often what you have is the nodes or your vertices on the one hand these are typically regarded as the actors in your network, the objects in your network, people, companies, contracts, cores, web pages, whatever. And with the edges then representing some sort of connection or interaction between those different actors. Like we are friends of one another, or we follow each other, or I like this post, and so on. So that's the common starting point. Typically, if you then look at the nodes, these are then a representation of something that has a real-life occurrence as well, like a person or a credit card or an address and so on. But then the first question is, am I working with a homogeneous graph, or will I set it up as a heterogeneous graph instead? Homogeneous means that your graph is unipartite in the sense that you only have one single node type. I only have, and that's the case in this example, for instance, all of these are customers. Every node is a customer. It's not the case here, because here I had both a node type for nodes that represent credit cards, and I had a type for nodes that represent merchants. How many of these node types am I going to introduce? The more that you introduce, the more richer that you can get also in the representation of these interactions between these different things, but probably the more sparse that your graph will become. So there is a trade-off at play here versus I start simple, homogeneous, versus no, I would like to make it more complex. But then sometimes the techniques will fail to give very good results. Most even graph neural networks assume that you represent your graph in a homogeneous format. There exist ones that work with heterogeneous graphs, but they're already a bit more cumbersome to set up. Very often, or there can be a difference between the choices that people make when they store their data in, say, a graph database, as we will see later, and then the graph that they will utilize to train their models on, which might be a simplicity or more simple version of that original graph that they had. Another question is, do our nodes have features? Well, yeah, sure, if you have multiple types, you could regard which type that node falls into as a feature of that node, but do they have other features as well? Like in the case of just now, yeah, every node has static information, like an age or an address and so on. In some cases, it's a single number, like an intensity of presence of that node. That can also be done. And then a question will be, well, does it make sense that I take some of the features that I have for these nodes, but that I do convert, or that I convert them to their own node type? Like I might have the address of my customers, but if I make address its own node type, and then I link customers to address nodes based on where they live, so based on what that original value was, then I start to see, hey, wait a second, there are addresses where a lot of people live together, for instance. So then you, by leveraging it as its own node type, you can also then start putting those interactions in as edges as well. Again, that's a trade-off. Like you can go extremely far with this, and you can start making everything its own node type. At some point, you will make things too sparse, and your learning techniques will start to fail. So start simple and see what goes. And similar for edges, that's then again some sort of connection. And same question: do I have multiple edge types? Does it make sense to have an edge that indicates a call between two people, or the total sum of calls or of minutes that they made in the past month, and then a different edge that represents how many text messages that were being sent? Or do I try to only keep it to a singular edge type and go from there? So also that's a design choice that you will have to make. Do my edges have weights in representing the intensity or the strength of the interaction, or do they have complete feature vectors of their own as well? Which is also possible, is that in the same edge, and then maybe you only need a single type, but that you do have a list of features in there, and that you say, well, no, I have one edge type, but the feature vector describes both the sum of calls, the average length of a call, the sum of text messages that they sent in this past time frame. So different ways how to construct this also depends on the tooling that you have available to construct the graph with. If you go full-on graph database, a lot will be possible. With more simpler tools, you will have to restrict yourself to a limited or a more limited set of representational constructs. Do my edges have a directionality? Can I have double edges, yes or no? Or self-loops possible, yes or no? Can I mix edges with a direction and edges that don't have a direction? Is there something as unidirectional, or is that not the same as two edges, one from you to me and me to you? Those are also choices to make there. Like if you think about a friendship network, if you're Facebook, yeah, you might follow me, but it doesn't mean that I necessarily follow you. So probably there I would utilize directional edges instead. A common kind of property of these edges is that they always, or that they only involve two nodes. So they have a source and a target, let's say. you might wonder, well, how about something like this? Is it possible that I have graphs where the edges involve more than two nodes? And indeed, that's possible. That's what's then called a hypergraph setup, but which is very rarely supported by available tools, including graph databases in most cases. There exist some GNN networks that can work with hypergraphs, but they are more created as a way to show, look, it's possible, rather than this is very frequently utilized. Now, that's annoying because let's say that you want to say, well, yeah, but these three authors, they have collaborated on the same paper. So if I can't do it this way, then how do I do it? Well, then you can say, I will model it like this, and I will just create pairwise edges between them. But it's not exactly the same, because with this situation, you do not know whether this is the result of all of these three people having worked on the same paper, or maybe number 1 and 2 work together on paper 1, number 2 and 3 work together on paper 3, and number 3 and 1 work together on paper, or 2 and the last pair work together on paper 3, which would lead to the same outcome, so you lose a little bit of information there. The other solution, if your construction tooling allows to set up multiple node types, is again to introduce a new node type and to say, well, I'm not just going to have circles for authors, but I'm also going to use diamonds in this case to represent papers as well. And then I can clearly say, well, authors work on papers and these three guys work together on this particular paper. So again, that requires a bit of thinking there, how you want to set that up. So also this situation here is kind of the same thing. On the left-hand side, we have a bipartite graph. We have two node types, and we restrict the edges so that edges only can go from author to paper. So we do not link authors together or papers together. This is already a quite revealing view. We know exactly which authors worked on which papers. If your tooling does not support multiple node types, well, then you need to set it up like this. And then the question is going to be, which weights do I then utilize on these edges? Maybe that can just be a binary weight. Yes, they worked together on a paper. Or maybe how many common neighbors do they have? Or what's the Jacquard distance between these sets of papers that they all work on? Also, question is, again, think about what is going to carry my label. In most cases, that will be your nodes. It will be your nodes that deliver the features and also the label. You want to predict on a node level. Is this node going to do something in the future? Is it going to be a yes or a no? In many cases, binary classification or a regression outcome, also possible. Cases exist where you can try to predict on the edge level. Depending on the technique that you utilize, you can either then try to do that directly with GNNs, that will be possible, or you try to flip your graph around so that you say, well, I'm going to make edges into nodes and then nodes into edges, and then you basically create like the dual of the graph, which can be done with things such as a line graph approach and so on. So even construction in many cases already a difficult task. And another question here, it's the same with tabular data, but with a graph, perhaps even more so. Yeah, how far back do I go? What is kind of the time window that I construct to deliver this graph? For our telco example, we might say, we will look 6 months, a year to construct the graph, but if we only called a lot in January, but then we completely stopped calling with one another, probably that data is not going to be as recent anymore or as informative anymore as what just happened in the past month. Another question is then, well, we can try to construct different graphs at different time frames and then try to create some sort of summary view that aggregates all of these graphs over time. And then very likely, to then still retain that the things that happened here are from way longer ago than the things that happened there. We're going to use some weighting, recency-based weighting mechanism again, just as when we did RFM, to maybe deliver the weights for these edges or adjust the weights of these edges. Maybe we start from the number of minutes that we called one another, but we are going to weigh these minutes based on how long ago that it was. And a lot of calling a year from now does not count for as much as a lot of calling very recently. So also applying tricks with those weightings of these edges to get recency graphs over time is also something that's quite common. Sometimes you can already start from a transactional database. So if you have like financial transactions or calls or things like that, you have like your edge list, say, that you can start from. But very often you need to construct or you need to go hunt for this data by, again, like always, merging different data sources together. And again, here there is where a lot of work happens in order for you to construct a graph. If your company or organization already has a graph database, then easier. But in most cases, this will come from like typical relational databases instead. Studies have been done, at least if you, with GNNs, it's probably a little bit different today, but if you look at the techniques that we'll see first, simplicity gets rewarded. It's a good idea to start with graphs that only have a single node type, have binary relationships that are even unweighted, non-directional, and just make sure that you have a sufficiently densely connected graph. That seems to help the most. So in some cases, people will also add in what they call pseudo edges, and those are edges for which you say, okay, maybe there is no immediate interaction that we can observe between these two people, but we are still going to add in an edge between them because they share a lot of common properties, for instance, or their behavioral patterns are very similar, or they just live close by, for instance, so that you try to make your graph a little bit more dense because that tends to help techniques a lot. Of course, we don't make a complete spaghetti bowl out of it either, where we basically connect everything to everything else. That would also be kind of belating the point a bit. Visually, yeah, we use layout techniques, like I already mentioned, to visualize our graphs, and we give colors and sizes to the nodes and so on. Layout techniques are quite interesting, but basically a topic on its own. There's also interesting stuff that you could do with, we have seen dimensionality reduction techniques that embed things on a two-dimensional map. You could also think about the potential interplay of a graph and these embedding techniques. Like if you apply an embedding technique, would it then also lead to a good layout and so on? But that's not discussed in detail. Yeah, another question is underlyingly, there is some matrix representation that happens, and again, you have different things to do that. You use an adjacency representation where you basically go node to node, and then the cells indicate whether there is an edge or not, maybe also the weight of those edges, or you can go for an edge list or an incidence matrix like this, where you have vertices in the rows and edges in the columns. We also don't go a lot deeper into this, but there are important remarks to make here. And one remark is, again, once we come to the point where we will start utilizing, because this basically represents the topology of the graph, if we want to deliver this to, say, a neural network, you can already feel, well, what are going to be the raw features? We will probably need a list of features for nodes, because they still have features, and then we need to represent the topology in some way. If I have a graph with 1 billion nodes, well, this thing is going to get quite large then, right? And not only that, probably a lot of these cells will simply be zero, and they will be taking up space for no reason at all. On top of that, I can swap columns and rows around here and get the same topology, but with a matrix that can look completely different. So that's maybe also not such a good idea that I would utilize this representation instead. So a lot of neural network libraries that learn from this, they will not just dump in a complete dense matrix like this, but they will try to go for sparse data structures, sparse representations, to offer that instead. So in a way, it represents the same information. This is what contains our graph topology, but typically as a software engineer, you would have to think pretty carefully about how you try to dump all of that into a GPU, especially also if you think about mini batching approaches, and when you say, okay, I need to predict on a node level, so it probably doesn't make a lot of sense that I try to have a network predict on this complete graph as a whole thing in like one go. Probably I'll have to take mini batches, kind of subgraphs from there that I can feed one by one, which are smaller, and that my GPU can crunch through without completely having to load in the thing. Okay, back away a bit from deep neural networks for a little bit. First, let's take a look at which more, let's say, traditional approaches that we can take on graphs. This is not rocket science. This is something that it's very similar to the RFM framework. You try to, in a tabular way, describe characteristics of mainly customers. Here, this is something very similar. Can we come up with good metrics that describe, and in a lot of cases, node-based, and that describe some sort of importance of that node, like how important is this node now in this social network. Now, important can mean different things, and hence you have different measures. If you think about a social network, is an important person a person that has a lot of friends? Like if you think about a Facebook graph, or that has a lot of followers. Well, yeah, sure, that's probably an influencer, or they have a large circle. If you think about spreading of gossip, if you're Facebook, or spread of misinformation, if you're trying to analyze that, would you then also look at those accounts that have a lot of friends? Well, probably less so. Then you're more looking at, because you might have a lot of friends, and yes, you could spread misinformation across your friend group, but maybe that is only your friend group, and then you're still quite far away from the network as a whole. So maybe there you would more be looking at those accounts which are like, act as spreaders, or have a good capability to spread stuff in the network. So you can think of different centrality measures that indicate different sorts of importance or types of importance for nodes. And hence why you get this list. There are more than just these, right? It's mainly to kind of show you the most well-known ones. Degree, also called local connectivity, simply means the number of edges that you have, right? So very simple, and then you can make a difference if you have a directed graph between your in-degree, number of incoming edges, out-degree, number of outgoing edges, and then you can normalize that again, like we did previously with TF, IDF, and so on, dividing by the maximum to get something nicely normalized there. That goes without saying. Example, yeah, number of friends, followers, these are typically active players in the network, not necessarily the most connected one, right? Again, if you look at this simple example, these guys over here, they have a high degree, but if I would ask you if I would spread the new COVID-25 strain, which one would you pick to start from? You'll probably pick the one in the middle there, right? So degree or local connectivity, one measure of importance, but not the only one there. The geodesic or graph theoretic center, that's basically computed as the node that has the lowest maximum distance to all other nodes. So what we do is for each node, we look, okay, I then look at every other node, and if I assume that I do take the shortest path to reach that other node, what is the maximum or the maximum length of that path that I can find? So basically, if I start with a particular node, and I want to visit all of the other guys, and to visit them I take the shortest path, what is my longest shortest path then? And you put that in every node, and then you look at the node or nodes that have the smallest value, and that's then your graph theoretic center. So the geodesic means the shortest path between two nodes, and we use the geodesic to calculate the graph theoretic center. But basically you can ask for the maximal path for all of your nodes, and that's also then another measure that indicates how close that you are to the center of the graph. If you have edge weights, then you can utilize them, obviously. If you do not have edge weights, then every edge counts as one step. So there is ways or different ways to instantiate these metrics. Closeness then also uses the geodesic. Also, you have different ways to write it down, but this is a common one. You say, okay, for a node X, n is the number of nodes minus 1, because we do not include X, so this is kind of a normalization that we do, and then we take the sum of every node which is not X. So again, we will visit each of the other nodes, and we will again just sum the length of that shortest path between all of these pairs. And that indicates closeness. And this basically indicates, okay, which of these nodes, the higher your closeness value is, because we have kind of flipped the fraction here. So now the higher your closeness value is, the closer that you are to the graph theoretic center, right? Also, the better your capability to reach out to other entities in the network. So this is more of our super spreader than here in the middle, which has the highest closeness value. Betweenness is then calculated as, a bit annoying to calculate if you need to do it by hand, also for a computer quite challenging, because here what happens is, again, if we calculate betweenness for a particular node, then we look at every other pair of nodes that we can find, not ordered, so we only count going from node A to B once, we don't also go from B to A, so we look at every other pair of nodes that we can find. We look at the geodesic between those two nodes, and then we count the number of times that the node for which we are currently calculating the metric for occurs on that geodesic path between all those pairs of nodes. And the more that it occurs, so then we just take the fraction, so 66 here is all the possible paths that we can make, and the geodesic, or the node in the middle here, will appear for 48 of them. Why not all of them? Yeah, if I want to go from this node to this node, I'm not passing by them. Right? So this is just the number of times that you appear on the shortest path and two other people want to communicate with one another, assuming that they take the shortest path through the network, right? These are nodes that have strong control and vision over the communication flow that happens across the rest of the network. What you can also see is that if you take these nodes out, if the betweenness value is high, that it's quite likely, and if you do that a couple of times, you continue taking out nodes, it's quite likely that you're going to break up your graph into subgraphs, into different pieces, right? Which follows, of course, of the definition of this metric. This is one which is sometimes calculated for nodes to get some idea of their importance, but is also commonly, as we'll see why later, can also be calculated for edges. It's the same thing, then for every edge, you look at the number of times that that edge occurs on the shortest path between all pairs of nodes that you have. There is also one which is based on, or which is called eigenvector centrality, or also sometimes called authority, but most well known as being utilized for Google's PageRank technique. You can implement this as a simple Markovian approach where you just have matrices that you continue to multiply until they converge to the final answer. So for this simple example, what do you need to get started from? A transition matrix, but you do that based on the edges, and an initial matrix that indicates your initial importances, but in this case, your 3 web pages, you have 3, so you're all going to give them 1/3 of the importance. You're going to start with the situation where they're all as important. And then this transition matrix, so the first row indicates Yahoo, right? And we see that Yahoo has an outgoing edge to itself. It has an outgoing edge going to Amazon, so it has 2 edges. We divide them, or so each of these edges gets 50% of the weight in this transition matrix in this first row, and so on for the others. You then take this transition matrix and this initial matrix, and you start to multiply, and you keep feeding in the result back into the multiplication, and you continue to multiply unless you, or until rather, you see some convergence there. And here this thing converges towards saying, Yahoo has 2/5 of the importance, so as Amazon, and poor Microsoft, they only have 1/5 of the importance. And you use that to rank your search results or whatever. This crashes horribly if your graph is not well behaved, and when you have too many orphans in terms of nodes, so nodes with only incoming edges but no outgoing edges, or you have nodes with only outgoing edges, or you have graphs which are not fully connected, so they are disconnected in pieces, then this doesn't work so well. Now, Google figured out a way. This also doesn't scale so well. If you have 1 billion nodes, then this matrix multiplication becomes quite unwieldy again. So what Google did, and this is how it became PageRank, they figured out how to get this converged result in a way where they didn't have to crunch through this enormous matrix multiplication, but they based it on the idea of random walkers. Basically what they do is, and this is something that you can run in parallel, you again start by giving all of the pages some kind of starting importance, and then you just drop in a random web server starting from somewhere, a random node, and you're going to have them randomly click on links, basically, until at every step they have a chance to get tired, and then they stop. And every time they click, they take a fraction of the importance of the nodes that they are coming from, and they're taking that with them and dropping it off at the node that they're going towards. And what they could prove is if you do this for long enough, that you have these walkers run around, that in the end you also end up with a nicely converged result. And we already saw last time when we spoke about node2vec, we already used or spoke about the idea of using random walks to generate sentences of node identifiers that we could then give to word2vec as well. So this random walking in graphs is something that you see quite commonly. What do you then do with these? Yeah, not every node is important in the same way. That's what these metrics show. Heather has the highest betweenness, Diane has the highest degree, and Fernando and Gord have the highest closeness. We can also calculate the PageRank values as well, where we would see that Diane also gets the highest PageRank value, and Jane, all over here at the edge, gets the lowest PageRank value. So Jane basically gets the lowest scores for everything. Yeah, what's the idea, or why do this? Well, if you think about visualizing your graphs and you want to make your nodes smaller or larger, or you want to give them a color, then obviously these are very oftentimes used for that. Or you want to filter your nodes based on this, or you're thinking about, I want to launch a viral campaign, or I would like to block the spread of misinformation, then these are metrics that are being typically utilized. Now, obviously, if you're now thinking, hey, but wait a second, if my nodes already have their feature vector, and I have this graph, and you're tasking me with come up with some representation for these nodes coming from the graph topology that I can use to feed to XGBoost or whatever, yeah, here you have them, right? You can directly utilize these 4 as features of your graph and dump them in. So that's also common. And of course, that trend of trying to extract features and including them, that's a trend that's going to continue. Another very common use case is that of community mining. And think of community mining as clustering on top of a graph, basically. Again, if you have a good layout algorithm, then you don't need to run community mining even to basically see, oh, well, there are like 3 large groups here. There's like this huge cluster in blue. Also, the coloring obviously helps. A huge cluster in red, and then there is this bunch of gray things in the middle. What are these? These are books, and they are being written more from a Democratic Party perspective or more from a Republican Party perspective, and then how they the links here are being made based on books that people or that were purchased together by the same person. So if a book gets purchased a lot by the same person, then we make a link and we'd see that people tend to stay in their echo bubble, let's say, and then you could maybe recommend them, okay, if you would like to escape your echo bubble, then maybe these 4 are good ones to read. It's still from the time of Bush, right? But you could repeat something like this today. Let's say that we want to do that in an analytical way rather than using a layout technique. So we want to find clusters. When we did k-means and we started from normal feature vectors, we said, okay, things that look quite similar, we want those to stick or to stay in the same cluster. And then between the clusters should look as dissimilar as possible. Here we work with graph topology. So what does similarity mean? Doesn't really work. So here it's based on the presence of these edges. So if you look within a cluster, you would assume these nodes to be quite densely connected to one another. That's what you want to see. If you look across clusters, there shouldn't be a lot of links going from the red group directly to the blue group, basically. So here it's based on your adjacency matrix. Now you could also wonder, are there techniques that can give me overlapping communities, or there are like different community mining techniques out there, just as we saw for clustering. They all tend to do things a little bit differently. You might have, again, your own preferences in terms of which result looks better to me, or is more stable looking or more revealing. Is it more based on maybe centrality-based metrics such as degree, but you might have clusters or communities all over the place, or is this maybe something more in line with what I expect to see? So this is also unsupervised, so it's pretty subjective in that sense as well. To kind of give you some ideas of how these techniques work, you have simple to more complex cases, but like 2 very simple ones is approach number 1 is you could try to take it as well, that's approach number 2. Approach number 1 is you use this betweenness that we had before. You do not calculate it based on the level of nodes this time, because then you would have to remove nodes, and that's not something that we really want to do. But you start by calculating the betweenness for all of your edges. And then, okay, here, that's going to be the one in the middle here. And then you say, well, you continue taking edges out until this whole graph that you have currently splits itself up into 2 graphs. And then you can continue to do that, and what you get is some kind of hierarchical dendrogram again, but over your graph. And note that previously we had said be a bit careful with hierarchical clustering because we always do it in an agglomerative manner because divisive is slow. Here now we do have a case where we are actually applying divisive hierarchical splitting to construct this community solution that we see. So this is also slow, even if you try to be smart by only calculating the betweenness of the edges that were affected by the removal. This is a slow technique, because calculating betweenness is quite expensive. There is a heuristic version of betweenness, which is faster, but still this will be relatively slow. You could also try to approach it as an optimization problem, and you just use your favorite OR mathematical modeling software, like something like a CPSet or whatever, and you say, okay, find me the minimal cut. So find me the combination of edges that I would have to remove to split up a graph into 2 subpieces, where you make the sum of the weights that I would have to take out of these edges, and if you don't have weights, they all count as 1, but where you make the sum of the edges that I take out as small as possible. And then again, you can start playing, because what you would see is probably you would only create, or you would split off tiny pieces of your graph. So like in a decision tree, we also said, well, the left-hand side and the right-hand side, we like them to be balanced in terms of number of instances that we have. So here you could do the same thing, and you could say, but I'm also going to add the number of nodes then in these 2 subgroups to get something more balanced. And if you have edge weights, then you might also say, well, I'm going to balance it based on the sum of the edge weights that every group has, and I'm trying to go to balance it in this way. This works, but again, or optimization, if you want to find the optimal solution here for large graphs, this can end up taking quite some time. So also this is a pretty computationally expensive technique. Now there are others as well, and still the most popular one is an algorithm for community mining, which is called, or a very popular one, called the Louvain algorithm. Sadly not our University of Louvain, but the University of Louvain-la-Neuve. It's a greedy optimization method. It starts by saying every node is in its own little community, and then it calculates a score. So this is based on a community quality score called modularity, a measure of the quality of a division of a graph into communities. And it basically says, well, I'm going to merge the 2 clusters that I currently have, or communities in this case, starting with the situation where I only have 1 for each community. I'm going to create the merger, or attempt the merger that improves the modularity score the most. And then I'm going to make like one node out of these two nodes that I've just joined together and repeat this process over and over again. So this looks very similar to an agglomerative clustering attempt, where I start from a situation where everybody is in their own little cluster, and I use some sort of improvement measure, not based on the distance here amongst nodes, but based on this modularity metric to find like the merger that always leads to the best improvement. Greedy, already a bit faster, so this tends to work better as your graphs get larger. Other attempts or other ways to work in a more agglomerative way is based on the concept of cliques. And a clique is a subgraph where every node is connected to every other node. Now, if I would ask you, find the maximal clique, so a clique that you cannot make larger anymore. If the clique needs to be completely connected or fully connected, your maximal clique that you will typically find, it's not going to contain a lot of nodes. Because we have 3 nodes, that's still okay. It means that we all have connections, or every member has connections to the 2 other members, so that looks like a triangle. If you have 4, then every member has connections to the 3 others, but that's already maybe a bit less common. If you have 5, 6, if you think about your friends on Facebook, do you have a group of 10 people where they're all 10 of them are friends with the 9 others? And that's probably already going to be a little bit more difficult. But you can relax that and you can say, okay, they do not need to be fully connected to be a clique. If they have like 90% of the edges that should be there, I'm also going to consider this a clique. So that's a k-core, a maximal subset of vertices that is each connected to at least k others in the subset. And then you can do your community building bottom up with that clique approach, where you say, okay, in the beginning, no one is in a cluster yet, so I'm just going to pick a node that is not yet in a community, and I'm going to see whether I can build a clique around them by following the connections and trying to expand from that until I can't grow the clique further, and I will say, okay, all of you belong to that single community now. And this is a technique that would also allow for, or that can allow for, overlapping communities as well, because even although I've already put some people in a clique on their own, I start them with someone else, but also that clique expands to include a couple of people that I've already put in a clique, so then I can say, well, these blue cases here, yeah, they're in both this clique, for instance, in this group and that other group. There are many other methods. They're all relatively slow, or they tend to be slow, so be a little bit careful with that. But again, the question is, what do we do with these communities? Similar things as we did with clustering, like for marketing analysis and things like that. It's interesting that we can identify clusters or communities in graphs. But also you could think of, well, maybe at the end of the day, these different communities, they're going to lead to features that I will utilize in some predictive pipeline. Maybe I will calculate the cluster or the community that you're in, and then I will utilize the number of members as a feature that describes you, or your cluster number or your community number, and I will utilize that in some way as a categorical level. So sometimes these community techniques can also deliver features down the line. Now, since we're talking about predictions anyway, in general, when you start from the situation where you say, okay, how can we now make predictions? Let's assume for a second that we will focus on making predictions for nodes. So the nodes have labels. There are basically 2 types. One is already the one that we've been basically hinting at already, is saying, okay, try to come up with features that you try to extract from this graph topology and just mix them in with the features that you already have. Easy, right, or understandable. But you could also ask, okay, but you're always going to lose that topology then afterwards. And who is to say that I have features to begin with? Aren't there techniques where I have just a structure or a topology like this one, and where I have nodes for which I already know the label for sure, so I have positive cases and negative cases, but I would like to use a structure to see, can I give a score to the nodes that are at this time still unknown, right? And very often this is also what you see. In many cases, having a confirmed negative label will be quite uncommon, but in a lot of cases what you will see is that you already have certain nodes that are already positive. You're not interested in predicting what they are going to become because they have already been lost. They have already committed fraud, they have already churned, they have already been infected, although with infection modeling, the already infected ones, they can also heal over time, so that's a little bit different. But typically for like churn cases and fraud cases, we say, okay, we have a bunch of nodes here that are already red. And then all the others, those are basically white, unknown. And I would like to calculate some measure of risk, how much under the influence are they of becoming red in this time frame that I will observe them for. And can I do so by only having this edge structure and having no other features? Of course, if you have other features, they will help, but aren't there techniques that do exactly this sort of thing? And then exactly you're looking at, well, you want something that can model the spread of these labels, the propagation of these labels to your network. So this is called network-based inference. We try to infer class membership of unknown nodes, which is maybe whether you will commit fraud or not, or whether you will churn or not, or maybe it could be a regression target, like what's the age of this node, for instance, or the price of a house, whatever. It's a bit comparable to semi-supervised modeling in that sense, but like I said, in most cases, you already have a couple of confirmed positives, historical positives you could call them, and you're kind of wondering how will they influence the currently not yet positive ones. Many of the techniques that exist in this space, they assume the presence of something called a Markov property, which sounds dumb, because a Markov property states that your outcome as a node is only determined by your first order direct neighbors, which if you think about it, I mean, here, if you start with this graph, why would the outcome of this white node only be determined by its direct neighbors? Say if these two neighbors are themselves already connected to a lot of fraudulent cases or red cases, let's say, wouldn't they also have a chance of influencing you through these blue guys? I mean, who's to say that that cannot happen? So this is not really something that we also utilize to limit ourselves. This is basically a first design principle that we utilize to invent algorithms, and then we bypass or we circumvent this Markov property very often by just saying, well, and then now you take this thing which assumes the Markov property and where you can do like one simulated step of what will happen, and you just repeat it a couple of times to model further spreading effects. So that's a way of how many of these techniques operate. Now, why does it work at the end? It also is related to a concept which is described as homophily. And homophily says that there is some kind of guilt by association or birds of a feather, not flock together, that should be. But it basically says, well, why does learning from graphs work? It's because of homophily. You tend to associate yourself with people who are like you, who have similar interests, who have similar social circles, who have similar fraudulent behavior, and so on. Even in a case such as fraud, you could think, yeah, but if I would be a fraudster, I would try to hide those patterns as much as possible. But it's not completely impossible to hide, right? If you think about insurance fraud, for instance, this happens. Insurers have found like rings of fraudsters where there is a group of 3 people, and they have been utilizing the same car, or the same set of cars, for already years, where every month you crash against me, I go to file an insurance claim. I get the money out, we share it, hopefully, right? Then meanwhile, I go take out a new contract with another insurer. And then the next month, I crash against you. And we repeat this, and we switch contracts over time, and we always do cash outs in that way. This is called crash for cash. So this happens, and then if you would look in the graph, you would see, yeah, but wait a second, across all of these claims, same cars which are involved, same people which are involved. The only issue there is the integration of the data between the different insurers. So by now, they already require to share data, especially for car insurance amongst them, so that they can exactly make those relationships across claims. Homophily then means if you have 2 groups, 2 labels, green and blue in this case, that if homophily is present, that I would expect to see more edges between nodes belonging to the same group than what I would expect to see if these edges would just be randomly there or not. And likewise, I expect to see less edges between 2 opposing groups than what I would expect to see if this graph would just be randomly connected. And then you can go to check, right? You can see, okay, how many edges on average do I expect between all the blue guys, the green guys, and between the 2 groups? And do I now see those results in a significant way, or is there something else going on? Is homophily going on? What do you see? In the case of fraudsters, for instance, we already saw the example of insurance, but also here, yeah, you do see that they tend to utilize a similar group of merchants in this case. They can't really avoid it. In this case, a customer who has a strong connection with people who have already churned, they are indeed more likely to churn if you track that over time and you look at these effects. If you make a graph based on call detail records again, and you just make a trade-off between what is the income of the person that performed the call versus what is the income of the person that they are calling, right? Well, there is a very strong diagonal relationship going on here. You tend to have a group of contacts that are in the same income bracket as you are. And you see this appearing all over time and all over the place again. So this is indeed a valid assumption in many settings. And this is, of course, what makes the technique work. If our graph would be simply randomly connected, then, of course, there isn't much that we can learn from that topology, right? So it's because it's not that we can. Now, which techniques can we then come up with to basically infer then the label of these unknown nodes that I have? Well, one of the very early techniques, and these are called relational learners, is called a relational neighbor classifier. You can laugh all the way to the bank, right? It's not spectacular at all. This is as simple as you can get. Well, just look at the neighbors and look at the known labels that they have. And then, yeah, if you have 2 fraudsters and 3 non-fraudsters, your risk of being a fraudster is 2/5. Wow, well done, right? Markov property at play. Not really what we want, right? Or maybe this is a first step towards something else, but this by itself is probably not going to lead us all the way there. Researchers are inventive. So they said, okay, we have this, but we also have a probabilistic version of this thing, right? And the difference here is that you just weigh the influence of all of these labels if you assume that this is not just a binary label 0 or 1, but it's basically the probability of being a fraudster. So you are a 90% fraudster, you're an 80% one, you're a 10% one, and you basically take that into the formalized weightings. Yeah, okay, but wait a second. And of course, our question is going to be, where does this probability come from? The answer originally was, maybe from a classifier that you already have. Yeah, okay, but if you already have features that you utilize to build your classifier with, then we're not going to do this. Then we're just going to take features from the graph and also dump them into that classifier. This is then going in a completely opposite way. Doesn't make a lot of sense. So, okay, you get published, fine. But at least it's a first step, because if you look at the other techniques, which are then propagation-based techniques and which are also modeled in diffusion or in network diffusion modeling, in news, opinions, rumors, and so on. If you look at Gibbs sampling, iterative classification, relaxation labeling, loopy belief propagation, and so on, that they tend to do something very similar as what this is doing, but coming up with an approach where they say, but now we are going to run this a couple of times after each other. We're going to make like a simulation where we loop this until we converge or we reach converged results, right? Because then even in the case where you might have a node which is connected also only with unknown nodes, well, no worries. Now if we are spreading this behavior, then we will probably converge to something that looks a bit better. And to give some ideas, these are not very frequently utilized techniques anymore, but they're quite, you can implement them yourself and play with them and see what happens. It's pretty fun to do. Gibbs sampling, for instance, says, okay, given that you have a network with known and unknown nodes, so we have a couple of already churned nodes, the red cases, and the others we don't know. Initialize every unknown node to obtain local posterior probabilities, but yeah, if we can't do that because we don't have features, we're just going to give them the same initial probability. So every unknown node has an equal probability of risk, right? And that's what we start from. We sample the class value of each node, so the binary label in this case, according to our probabilities, and then we randomly order them. And then we're going to basically visit, in the first step, all of my unknown nodes. And I'm going to apply this relational learner that I just saw to basically get an updated probability of you being at risk, of you being a fraudster by using this relational learner. That means that the probabilities for my unknown nodes will have changed. So I sample their class value again, I generate optionally new random ordering, and I continue doing this over and over and over again. First, I do this without looking at anything, and then I do this for a couple of iterations more, and then every time I sample this class value according to this probability, I keep track of whether I sampled you as a yes or as a no, and that tally of yeses out of the total samples that we performed will give us the final class probability estimates. This sounds okay in theory. Problem with this is that depending on how you set this up, and depending on how much you repeat here, and depending on what you use to initialize, and depending what your network looks like, and the imbalance between known positive cases and known negative cases, this doesn't always converge that well. So this, in practice, this requires a bit of tuning to converge well. And also in the case where you would like to start with the situation saying, well, I only have already positive nodes. What will happen if I have this converge too many or for too long? My whole graph will color red in that case. So I have to stop somewhere in the middle. I can't spread continuously, right? So probably you would have to not repeat for too often to get something in between, like, okay, if you run this for 1,000 times, then the spread has gone so far already. Okay, you can do that, but it's a bit of a drawback with these techniques. Personalized PageRank is a bit, or is a very, or is still a quite commonly used technique. And this is exactly an implementation of PageRank as we saw before. So we have random walkers in our network, and we have them walk around, and they carry importance from one node to another node. Personalized means that every time you restart and you dump your walker in your network, that you do not randomly pick any node for them to start from, but you make a weighted sample, or you do a weighted picking based on, again, some vector that you have set. And what is then commonly done in cases where you say, okay, I have nodes which are already positive, that you randomly pick one of these already positive cases to start from. And you try to model how they will spread their influence through the rest of the network. So only these have an initial importance score, but then basically you start from here and you randomly walk around, and then basically the numbers that you get at the end, those can be utilized as your predictive scores. That tends to work much better than earlier techniques like Gibbs sampling. Also propagates better in many cases, and works better in a situation where you just have a group of already fraudulent or churner nodes. So that looks, for instance, something like this. There are newer techniques as well, like in the paper, learning from labeled and unlabeled data with label propagation. They utilize this in a semi-supervised setting initially, but then people already or found out, hey, but you can also apply this on a graph. So similar idea, you have a couple of unknown nodes and you want to see how it spreads around. Similar drawbacks as well. Propagation sometimes not always so stable. If you try to apply this to a one-class setting where you only have positive cases, but you don't have confirmed negative cases, then those can be difficult. Also very difficult is to think about how this would work if your use case is about regression. Like all of these nodes, for some of these I have a numerical target which is confirmed. What will the target be for the others? Also harder to find implementations in that case. Here you can see another of, or a couple of other more modern label spreading or propagation-based techniques. This one from 2020 is kind of the newest one. So implementations for that exist, but they all try to model spread in a similar way. Now, if you're thinking, okay, I get it. If I only have a topology and some known, unknown nodes, I can do something. But at the end of the day, you're just kind of modeling spread in a graph. And let's be honest, very often, it's probably going to be more likely that you start with your nodes for which you already have features for, than you start with a situation where you only have a graph, right? And so that's the reason why the second approach, featureization, is of course the more common one, right? Even considering, hey, I'm actually still free to utilize these relational learners that I just introduced, or I use something like personalized PageRank, I take those scores, but instead of using them then directly as my final predicted outcome, let me also use these PageRank scores as yet another feature that I just give to my favorite classifier together with all of these features that I already have for my nodes, and probably together with maybe these centrality metrics like degree and betweenness and so on. And indeed, that's of course the thing that's been most commonly done. Liu and Guitor in 2003, they called this relational logistic regression, but again, not very fancy. They said, well, you probably already have customer attributes, keep them. And then here are some ideas how you can featureize from a network. And by the way, what you have is classes or confirmed classes of your neighbors, so you can count these, and you just combine these with your normal features, and then you use logistic regression. Why? Because you're 2003. Nothing says that this has to be logistic regression. So this is, of course, a strategy that's been most commonly followed and also still in industry if you want to keep it relatively simple. So you just count the number of snow fraud, and so on. Careful, though, and we will talk a little bit further about this, this thing that we are doing here of, we are counting the number of fraudsters and no fraudsters. If your labels come from something that happens in the future, no data leakage, right? So here, actually, the counting that's being done can only be based on stuff that has already been confirmed. Again, right? If you're doing that based on labels that still have to appear between now and the coming months, yeah, you're cheating again, right? You're featureizing in a way where you're taking future information and bringing it to the present. So be very careful that you only utilize information that you know at the time of data extraction, at the time of inference, at the time of graph construction as well. So that's something to keep in mind. But then you can, of course, start thinking about, hey, wait a second, you have your own age. We know who your friends are. Maybe having the average age of your friends as a feature might be valuable because maybe there is a large difference between that and it can say something about the outcome that we want to predict for here. So yeah, come up basically with any of your own smart ideas as well based on the features that you do have, and of course use any classifier that you want. So then you get things such as we can start thinking about the total degree as a feature, and maybe for these 4 guys we already know that they have committed fraud, so what's your degree to fraudsters, what's your degree to currently still legit nodes as well. We split that up. Let's count the number of triangles that you are involved in as a node and how many of these triangles are completely fraudulent, how many of these are completely legit, how many of these are semi-fraudulent, what's the geodesic path between you and your closest fraudulent surrounding node in the neighborhood, how many one-hop paths are there between you and a fraudulent node. So in other words, how many paths of one step can I find that lead me from you to a fraudulent node? How many 2-hop paths, how many 3-hop paths? And then, okay, let's put in closeness as well. Let's put in betweenness as well. Let's put in PageRank as well for all of these nodes. And then you have your normal representational feature vector per node. So that's basically it. And then the idea is, okay, I keep my network simple. My nodes are my label carrier and my attribute carrier. My edges very often non-directional first, because then that keeps it easy as well. And then domain-driven features such as, oh, well, I have your promotions, but I'm also going to bring the promotions of your friends to your feature vector. I'm going to aggregate in that way based on the friend level, because that can also help. And then, if you still want something that is able to look a little bit more globally in a way that takes this propagation or spread mechanism into account, okay, that's this personalized PageRank that we then had, and we also add that in as a feature as well. This was a decade ago, and actually in industry, this is still very common. So this is a very common approach still, and what you do see is, yeah, you then make choices between, this is about social security fraud, so the nodes here are companies. Okay, do we keep it as this? Maybe still better to introduce a separate node type. The diamonds in this case, they represent employees or board members. And so for some board members, once they have been involved in a fraudulent company, they become fraudulent as well. But basically, we want to predict for these circles here. We set up this whole featureization strategy. So you have a graph like this. Some of your companies, they have already committed fraud in the past, and you have a lot of information about these companies. Links basically represent that this employee is currently present at this company or doing something for this company. You link the edges based on the recency of the association, as we saw, and then you start featureizing, as we have introduced, and you calculate personalized PageRank, you count triangles, number of triangles we have already introduced in the previous example as well. So something that was done here is, since here you can only connect employees to companies, how do you make this network then a little bit more dense? Well, you can say, okay, for every pair of employees that have shared a company that they work at, we're also going to create an edge between those employees. And now we also have edges between employees. So you make your graph a bit denser, you run personalized PageRank, you run these featureization techniques, you model the spread by using personalized PageRank, and at the end what you see, and this is confirmed by many similar studies as well, is you can then contrast 3 ways of working. You could say, okay, what if I only use my static features of these companies and I go the classical route, I don't use any network information at all? Typically, or you hope, you will see, you get like a pretty solid result in terms of a local regression model or a neural network or a decision tree. Okay, so that's your starting point. What if I would only use network information? So only features coming from the network, but no features that are derived from these static properties that I had for these companies. Yeah, you will get an AUC which is above 50% typically, but not that good. But then, of course, the question lies in, okay, but what about a model where I combine all of these features together and I dump those into my random forest or even my logistic regression in a simpler case? Well, typically that will give you a little bit of a boost on top of that just purely local model that you already had. So that's good news, means that we can utilize this. Before we go for a break, I again mentioned, be careful with this data leakage thing. If your ROC curve suddenly shows something like the black line over here, you know that you have messed something up, right? So you know that you did something wrong. So again, all your feature engineering should happen after the train and test split. You can run something like personalized PageRank either on nodes for which you already know that they have committed fraud, or you already know that they have already churned. But You could say, well, maybe something else that I need to consider, this train and test split, what does it mean for if all these instances that I have are also nodes in my graph? It's not really appropriate that I cut this up into train and test, which would also mean that I cut up my graph into two pieces like this. It sounds ideal because you might say, then you can go crazy in terms of featureization approaches on your train graph, and then you re-execute them on your test graph, and that should be stable. But of course, if you start cutting in your graph, you're breaking up relationships that do exist, right? You will change the values of the features that you extract, both from the train graph and then hence also in the test graph. So networks do make it hard to set up a solid validation strategy for them. This is also related to the point of transductive and inductive learning, but I will come back to this slide when we have introduced GNNs, because for now, that's still a little bit too annoying to discuss. But basically, like this train test split, a question there is, what do we do? The best strategy is basically, or the only viable strategy is, well, you have two ways. You could say, well, we could randomly hide a part of our graph at least, and not utilize these nodes. But also, again, if we don't utilize them in featureization, we are kind of breaking up the structure of our graph. So that's not ideal. The other situation where you say is, well, I'm just going to extract my train and test set by working at two different periods in time. And I'm going to use the 1st of January last year ago as my train set, and hence also the train graph. And then I'm going to move forward in time, and I'm going to construct a new graph at that point in time, where probably I look backwards to extract my edges from. And construct a graph there. Now, yes, those two graphs will, in some sense, they will overlap with one another. If we are calling each other a lot now, probably a year from now, we might also still be calling each other a lot. What you mostly want to protect for is you also want to make sure that you can handle the fact, what if nodes appear in your graph? What if nodes disappear from your graph? Is all the rest of your pipeline robust against that? Can it handle that? Can it deal with that? So this is a little bit of an annoying aspect. Probably the most also key tip to give is every time you're using like labels of nodes, as was the case in this example, for instance, if you're using the label of nodes to featureize, you need to use the label that you have already established at that point, not a label that has yet to establish itself in the future. Now, mistakes have been made against this, also in papers, by the way, so don't think that it doesn't happen. So be a bit careful, extract graphs at different points in time, which is also a good test to see whether you're capable to put the idea of, hey, can we now get the latest version of our graph? Yeah, at some point you will have to put that into production, because if you plan to use this model to make predictions in the future, that model will need the graph to perform its featureization steps on. So it's not the case that you can just construct a single version of your graph and then continue to use that for the rest of time. Also, that graph will have to be kept up to date as well. So do take that into account, that in terms of pressure on, let's say, maintaining something like this does become higher, of course, than just working with your standard features that you would have utilized in a tabular setting. Okay, we will then talk about graph neural networks, but first let us go for a 10-minute break. Okay. So we introduce graph neural networks now. Basically, yet another neural unit that we will introduce, like the architecture, like the fully connected one or the RNN one, as we saw previously, or the convolutional one before as well. The way how this started to evolve was not immediately by going like full-on GNN style. Like I already mentioned, that early attempts in this space basically started by experimenting with, let's take this idea from PageRank, where we perform a random graph, where we start at a particular node, and then we randomly walk around following the edges until we want to stop based on some probability, and then we restart and we generate these walks. If you don't have weights, you can just sample randomly from the neighbors. If you have weights, then you can utilize those to include in the way how you walk around by using that as a probability corresponding with the weights. And it's this I already mentioned. This gave rise to Node2Vec. It's also exactly the same thing as what Deepwalk introduced, a very similar approach So early approaches that try to apply deep learning on graphs, starting with we generate sentences from random walks, and then we utilize something that looks heavily like Word2Vec to again now not get an embedding or a representation per word, but for each node. So this is deep walk, unsupervised. We learn representations of nodes, although theoretically you could also do this then for edges. Instead of writing the node identifier down, you could also keep track of sentences that consist of edge identifiers and embed this as well. Got numerous variations like graph, Sage, and so on, extensions. Difference with, so this is deep walk. So it's basically Word2Vec, same thing, but we construct random walks, and then there is this skipgram that shows up, which we already saw previously. What did Node2Vec change? Node2Vec comes up with basically a bias for that random walk, where you do not make it completely random, but you it defines a second order random walk, which you can then set two parameters at P and Q, which helps to steer the random walker in a certain way and to kind of indicate a preference to stay close in the neighborhood of a node and to maybe do some kind of breadth first random walking versus more something that looks like a depth first, where you try to move further away from the node that you came from in every step. That's nice. Basically what this indicates, implementing random walk for a graph is very simple. You then install GenSim to generate your representations. You're done. And then you can start thinking about how do I take this code and I try to play a bit with the way how I walk around in my graph. What then happens is just as we saw with Word2Vec, that here then you get a representational vector for each of the nodes in your network. And then tada, what can you do with those vectors? You use k-means to cluster them, and you basically get some kind of community mining result. I'm not going to say for free, but something that still scales or does scale pretty well even to larger graphs. So, and then if you start playing with the way how you steer that random walker, you can make these communities look more or be based more on structural properties. So that's what you see here, for instance. Here the random walker generated representational vectors that correspond heavily with a solution that community mining or community detection would give you. Here you can see that the way how the representational vectors have been generated, that corresponds more with degree as an underlying kind of mechanism. So maybe more based on structural topology instead. Now, it's still computationally inefficient enough. I mean, yeah, you need enough random walks in order to run Word2Vec, and as your graph gets larger, probably the number of walks that you need will scale not in a nonlinear way, but okay, at least it's something. But also, this is purely based on the structure of our network again. If you already have features for your nodes and your edges, then these will not be included in there, although you could think of how you define your item set of nodes and maybe also doing something with the features there and dropping them in as well, but it's going to be difficult. But most annoyingly is, and we saw this also with Word2Vec as well, is that this is just like a pure non-parametric style of embedding where we directly try to learn the embeddings. That's also what Word2Vec did. It's not like a parametric design to basically transform a raw representation to an embedding. So here too, if you say I have these vectors for my nodes, and probably they will work pretty well if you then just construct a train test split on these vectors, and you then give them to your favorite classifier, they will actually do a good job, right? But still, you could say there is a little bit of leakage in there because you waited until you had extracted your representations before then splitting that set. Theoretically, you should have started with two different graphs, a train graph and a test graph. But that wouldn't really work because if you run, just as with Word2Vec, if you introduce new words, your whole representation changes and pivots. So also here, if new nodes can show up over time, what's the representational vector for them? You wouldn't know, except if you run this whole thing again. And you could get clever, and there are ways where you say, now I want to just generate walks around this new node that has appeared, and isn't there a way how I can just add this to my embedding layer without having to retrain all my existing embeddings? You could play around with that. I've played around with that myself already years ago, but architecturally speaking, it's not really like a solid approach in that case. So it's unsupervised, also not parametric. So same thing here. as we saw with kind of our textual representations with these RNNs, and also what we saw with CNNs, like you do that global average pooling at the end, you get that vector for that image. That is a result of a process where you start with a raw representation, and it's the network inherently in itself, in one of those layers, that tries to iteratively construct an embedding in a more parametric way, rather than just saying, well, here you have a matrix of weights, try to fill them in, and the number of rows is limited to the number of items in that item set. So same question here. If I start with a graph, isn't there then a way where I can give this whole thing as an input to a neural network, where I need to give both probably something that describes the layout of that graph, so something that looks like an adjacency matrix but which is more sparse, where I might want to give node features that I already have, even edge features that I already have, perhaps even graph level features that I already have, something that's related to the complete graph as a description. And likewise, can I then build up across a couple of layers? Can I then say, dear network, starting with this raw structure, please construct for me a representational vector, either for all of the nodes, or maybe for all of the edges, or maybe both, or in some cases, maybe create me an embedding, a representation for the graph as a whole. And then in the last step, again, the idea is that we can then take this and then push this through a sigmoid layer or whatever in the last layer and say, well, then your last step is to, based on this representation, give a prediction, a probability for all of these nodes, or for the whole graph, or for each of the edges, and so on. So once I have these embeddings, I could easily, again, utilize them in whatever downstream task that I have in mind. So if I want to do binary classification, if I have a way to extract node embeddings, then it's just a matter of then sticking some MLP layers at the end and getting my sigmoid output. Exactly the same as back when we started from with that AlexNet CNN, that did exactly the same thing. So how do we feed this graph as an input? Well, I've already stated it. We need our different components. So we need node features, edge features, and global features, graph features. So that's the same as before. Those are basically all feature matrices. So that's going to be quite okay. Connectivity, or the topology of the graph, that's a bit more complicated. So again, here you might say, can't we just use that adjacency matrix? But like we already said, this is not such a good representation because it's a very large thing, a very sparse thing, and you have different versions that you can construct in terms of different adjacency matrices that connect the exact same underlying connectivity. So what is typically chosen instead is that we use a sparse construct, a sparse matrix as an adjacency list, and which just describe the connectivity of an edge between two nodes as a tuple in the Kate entry of a list of edges, basically. That's a bit of a technical detail, just goes to show, like, if you ever wonder if you install PyTorch geometric and why does it need sparse tensors, it's exactly because of this reason, because it wants to get like a better representation for that connectivity. But okay, let's say we just pretend that we give the adjacency matrix, some input comes in that raw form, we have made it a bit more clever in terms of memory layout and representation, but that's basically what we give on the input sides to our network. So we have a matrix describing for each row being a node, so node 1, node 2, and so on, describing features that we have. We have an edge list or an adjacency matrix. We might have edge features, we might have graph features, but we could say that's our basic starting point. We have a matrix where we have our features for each of our nodes, and we have that adjacency matrix. I would like to come up with some sort of structure where this gets transformed automatically to a good representation for all of the nodes that I have in this network, in some way also utilizing this, obviously, right? Not just simply using this by itself, where if I would then add an MLP on top of this, where I can make like final sigmoid predictions that come out of there. Okay, fine, how do I do that? Well, every time you're looking for, hey, here is something that needs to learn a representation starting from raw input features, and I don't just want to take the embedding strategy because my item set size is not pre-known and limited. Yeah, your other approach is then basically, well, the next starting point is just to say I'm going to utilize an MLP also, right? I have my input features here. I'm going to run this through a first MLP layer where everything is connected here to everything else, and then based on the dimensionality of this layer in terms of output size, well, this is my representation, and I can dump in a node on the input side, and I get 6 numbers out of there, just like our autoencoder did as well, with that intermediate layer there. That was also a representation that we then encode, right? We could do the same thing here. Ah, yeah. Well done. So basically, if you have one MLP layer and xi0 or your starting features for node I, indeed, if you pass them out, then you get an embedding xi after layer 1, right, of a chosen size, and then you can move that through a different MLP again and through a different one again, so you can do this exactly like an autoencoder did until you get xik, because you slapped in k layers there. Yeah, well done, but you have just built an autoencoder, or the encoder part, at least, on top of your input features, but I'm not using connectivity in any way. Now I'm just basically transforming my static features that I have for each node, and I'm transforming them to an intermediate representation in a more compressed format, also very likely, just as what we did with an autoencoder, because compression helps learning or forces learning, but I'm not using my connectivity in any sense. Another issue is that now I'm only using nodes, and I said at the end I want to give features of a node, create a representation, and from there give something between 0 and 1. But let's say that you also have edge features, and you also want to give them in, and you have more edges than you have nodes. So for every edge you will get a representation. But at the end, you still would like to get a prediction at the node level, not at the edge level. So how do you align that different dimensionality there? In other words, or maybe vice versa, you might want to predict something on the level of edges, even not having any features, but you might say, but yeah, for an edge, I do know the two nodes that are connected to it. So I can build up first a representation for these two nodes, but then it's this, I would like to use them both to make my prediction. And again, that's not so hard. You can think of pooling strategies, obviously, to do that. Couple of examples, right? So let's say I do want to predict something at the level of an edge rather than at the level of a node. No problem. I give these two node features as inputs to my network. I have representations for both of them. What can I do before I slap my final layer on top of that is just to concatenate them together and make one long vector. I always have two. So here the choice to concatenate would work, right? I always have two nodes for each edge that I want to predict on. Likewise, let's say, no, I want to predict something on the level of nodes, but I also have edge features, and for this node, I have 5 edges that it's connected to. So I could first also transform this using a separate MLP stack into a representation for each of these edges, but then I'm looking for, can I now bring these 5 vectors together, then maybe concatenate them with the representation for that node to perform my final prediction on. This concatenation would work. Here, not really, because some nodes have 5 edges, some nodes have 3 edges. So I can't just make a long vector out of it, because then my dimensionality is again not going to match up. So here, what pooling typically then recommends is, okay, then you just gather these representations for these edges that are connected to your node. And then, a bit similar as what we saw previously, what people did with Word2Vec as well is here, just average them or take the sum of them instead. And use that then as the representational vector for this bunch of 5 edges connected to this node. So this is relatively easily solved. So in the extreme case, you might say, I have features for nodes, I have an adjacency matrix, but my final prediction needs to be made for the graph as a whole. I don't want to have a representation per node and then have a prediction for each of those, something between 0 and 1, but my final prediction is on the graph level because it represents a molecule, and as node features I have which type of chemical element that it is it carbon or oxygen or whatever. My edges relate to how they are linked and maybe with a weight indicating the strength of the bond between them or the type of the bond or whatever. So here too you could say no problem, for every node that you fed in at the end you will get some representation for that node, same for your edges. Now you want to make a prediction at the graph level. Well, basically what you can do is some sort of extreme aggregation where you say, well, either take the average of all of these things, right? Or maybe first for the nodes, for the edges, and you concatenate those two and you make your final prediction based on that. What you could also do, and this is exactly the same thing as what we did with CNNs as well, except that they're intermediate representations. When you think back of the filters that these neurons apply to generate their convolved output maps, the representation there was something two-dimensional, right? But also there, we continue to stack this. And at the end, we said, well, now the final representation that we get after this global average pooling is we're going to reduce this two-dimensional map for each of these outputs down to a single number. And then basically this whole thing becomes our representational vector. Well, likewise here, we could say continue stacking MLPs, and the last MLP is just going to create a single number. And then this whole thing can become a representational construct that we then give to a downstream MLP as well. So there's ways how you can transpose and play with this to make this work. It's not really this that is the issue here. Even if we would forget about topology and we would just say, hey, I give you 5 nodes, but actually I want to have a prediction for the collection of the nodes as a whole, you will start to understand, okay, first build up a representation for each of the nodes, and then I will have to average them in some way together to like a singular vector that I predict on or do something with. That's the same could actually happen with tabular data. Like I could tell you, I don't give you a single instance as an input, but I give you a bunch of instances. I would like to get something for this bunch of instances instead. Like here are n people described by their features. How likely is it that they were in the same academic program together? And so the prediction is on the level of a bunch of people rather than separately for each of the persons. Our larger problem to solve, and the more important one, is, how do we utilize this connectivity thing? How do we utilize the network structure that we have? Especially when you think about when you build up these representations that you're doing now. And again, let's assume the easy case where you say you start or you build them up for nodes. You start with the static features for a node. You can transform them in a couple of encoder stacks. And none of those steps does that MLP layer have the opportunity to say, not what are only the features that you have, but what does your neighborhood look like? What does your environment look like? Right? What does the graph look like? And it makes sense that since we are working with a graph, that probably when I'm thinking about how should I update your input features to some output representation by doing some, basically transformation on top of them, because that's all these MLPs do at the end of the day, that I not just look at that node in isolation, one by one, but I also give it like the surrounding information of that node, the subgraph around that node. So we need to solve this. The way how GNNs do this is by a concept which is called message passing. So that's something that you typically see. There are other ways as well. These are typically also called spatial methods. You have spectral methods as well that basically try to encode the whole connectivity of a graph and putting it in a layer to do this. But message passing is a little bit simpler in terms of concept there. We will always apply 3 steps. So we're going to come up not with an MLP on top of our node features, but we're going to come up with a new kind of unit that creates its output in a different way and is going to apply message passing. And message passing means that we do the following steps. For each node in our graph, we're also going to look at the neighboring nodes. And we're going to take the features of those neighboring nodes. In layer 1, those embeddings for the neighboring nodes are also just their starting features that we gave in the input. At layer number k, the representations for these nodes will get updated and changed. So in that layer, when we take the representations for the neighboring nodes, they are also just representational vectors. These are the messages that they send to a central node that we are looking at. Because the number of neighbors might differ, and it's not always the same for a node, again, we need to apply some kind of aggregation there. And very often people say, well, just sum those messages together, take all these vectors and sum them together, or take the average. And then that average pooled message, we pass them as a last step through an update function. And typically there, that's then going to be that looks very similar to an MLP again. So it's basically an MLP with a couple of extra steps. An MLP that says, well, don't just use the features of this node as an input. First, gather the features of the nodes around it, bring them in, sum them, and that's what we utilize to pass through this update function. So generally speaking, this would be our a very generic formulation for what such a unit could look like. Single unit. So we will again put multiple of these neurons, or we could put multiple of these neurons in a single layer. But like, let's say, okay, in layer K, what do I need? Of course, I need the features of node I that we are looking at. So I'm constructing an updated representation for node I. And I need to know, okay, in the last layer, what was the output that this thing produced in terms of intermediate representational vector. So this is just a vector, this X thing, for this node I. So that's who are you. Then I'm going to look at all of your neighbors. And I'm going to bring in their features, and this should be J instead of I, sorry for that, so this is not I, but J, so that's a small typo. So I'm going to look at, no, it's here, sorry, a bit confused. So I'm going to look at your features, right, of your neighbor. If I have an edge weight, I might not have that, so then I can forget about this part, but let's say I might have an edge weight, I can also stick that in there as well, so that's another input that I gather. And I'm also looking here as well as my own features as well. For each long vector that you basically get here, because these things are just concatenated together and have always the same length, because I know the k-1 layer produces 8 numbers for you, so also 8 numbers for each of the neighbors that you have. You might have multiple neighbors, but here for each neighbor, I get the same kind of gathered message. That's the whole thing here in blue. So that's the message that I get for this neighbor. I will then aggregate all these messages, but what I could also do before I aggregate my messages is that I apply also a message function or gather function in between, which you should think of as this could just be an MLP again. So this takes in this tuple of 3 things and transforms it first. And here, this is why it's a good idea to also look at your own features, because then this MLP can learn based on who you are and based on who your friend is. Here is probably the best way how I should now execute this transformation here. And based on the weight of the edge between you, if that's very low, then maybe I will not do a lot. If that's high, then maybe I will change a lot, and so on. So this is optional, but you could say, well, I'm going to transform each message that I get in. I still have multiple messages. So then there is the step of aggregating these down to a single vector. And this is sum or mean, right? And then here, this combination of this entire entity is again a vector of a known length. And then again, I can stick an update function in front of that, another MLP, to perform that final transformation and the final update of your representational vector. So the MLP that we had before, when we were still doing this thing, basically the instantiation of this generic formula was then, well, if you want to get the representation for node I at layer k, what do? You take the representation that the previous layer gave you, which is 8, 10, 12, who knows how many numbers, depending on your dimensionality of that layer, and you pass them through a new MLP, right? And to get the updated representation. But this thing only uses my own features, basically, down the line. Here we have something that also gathers information from the neighbors that I have. Annoying, you might say, I'm only looking at the immediate neighborhood, so that's that Markov property again at play there. So don't I need to look further than just, okay, it's important to know who your friends are and take their features in, but shouldn't I also look at the neighbors of your neighbors, right? We can make another representation or rewrite this a bit again, and we could say, well, a simple implementation could just then be, I'm going to look at all of your neighbors, and by the way, also include yourself, right? And just do a matrix multiplication with some kind of weight matrix, which is also of fixed size, because I know the number of features that nodes have, right? So this is just a weight matrix with a known size, which I apply on all of the neighbors. So the number of neighbors might still differ, but no worries. I sum all of these results. I pass that through an MLP layer again, and that's my update. So I'm not using edge weights here in any way, because I assume that I don't have them. And I'm also not first transforming all of the inputs that my neighbors gave me with this separate thing here. I say, no, that's not necessary. That can be basically handled by that final update layer anyway. It's not perfect yet. We can make some further adjustments to this. But this does reveal something that we know from previously, this kind of idea of my plan is to apply a bunch of small weights to all parts of something, and then I will make a sum of products, right? This starts to look, or starts to remind us a little bit of how a convolutional neural network applies its filter. There also the idea was, we are going to take this filter, we will slide it over the input image, and we will take the sum of products that we get there when we apply this filter. So this starts to look quite similar, and hence this is also the reason why people will say, well, what we are doing here with this approach, it is as if we would be taking or applying a convolution, but now not in a regular domain, meaning something that has a well-defined grid and the same number of neighbors no matter where you are in this grid, And you could connect the pixels that you have as a graph as well as you see on the right-hand side. Except with a graph, the neighborhood of each node does not have the same number of neighbors. But basically what we're wanting to do is still we want to apply a convolution where we say, well, take all of the neighbors that this pixel slash node now has, and we make some sort of sum of products to generate like an updated representation for this there. So hence why message passing applies convolutions in irregular domains. We also saw with the CNN architecture that even although we make our filter small, and there we said, we take a 2 by 2 even, that's actually okay, because if we stack multiple of such layers on top of each other, by the end you come to layer 10, to construct that 2D output map, you have basically looked at a very large input space of your image. Same here. It's okay if in one layer you say, I can only look at the immediate neighbors, but if we stack layers on top of each other, then the neighborhood also grows in size as well. So you also get this widening receptive field here too. So that's why we can limit ourselves at only looking at the immediate neighborhood. One thing that we didn't really do that well, I lied a little bit with this weight matrix, and I said, well, this I is pretty similar, right, in terms of length and so on, but still, if you would try to write this out, it wouldn't work, because this weight matrix, what this subscript here reveals, is basically saying, okay, it's always the same number of weights, but you do need a separate weight matrix for each JI combination. They're all the same size, but still, it doesn't make a lot of sense that you would have a network where you say, for each pair of nodes, I want you to learn a separate bunch of weights, or for each pair of edge, basically, that occurs here, right? Not for every possible pair, but only the nodes that are connected to one another. Why not? Well, you lose generalizability again. Tomorrow you have a new node. You don't have weights for this new node that pop up there if it's connected to your network. So the only thing that we kind of need to change is we can't basically say, let's pre-code or pre-learn all of the possible weights that we can have for each JI combination. We need something that's more generic and flexible, where we say, okay, I shouldn't really look at the fact that your node 5 and node number 3, what I need, and hence why we need this gather function instead, where we need something where I can say, no, you don't learn weights specific for every index I and j. I need a separate kind of tiny MLP layer, basically, where I can give the features of I and the features of j as inputs, and I get a representation. And then no worries if tomorrow there is like a new node that appears, it should still be able to apply the transformation for me. But once we implement that, we basically have a convolution in an irregular domain. That's what spatial methods do. They basically implement, so if you look why are there so many GNN units available, they all come up with different ideas of how to instantiate this thing here at the top. Some make it more complex, some make it simpler. Also here we have kind of said or assumed I have edge weights, but where are my edge features? Maybe I also need to pass them in over there. Okay, then you make it more complex. What if you have a heterogeneous graph and you might have different types of edges and different types of nodes? Then it also becomes a step more complex. But this message gathering, aggregation, update kind of approach, that's something that you see in all of their implementations. So we base ourselves on connectivity, we message pass between neighbors, we focus this around a given node, it's flexible, scalable, and how do we widen the receptive field is by just stacking more layers on top of each other. Spectral methods, they do not try to widen this neighborhood by stacking layers like CNNs do, though you have spectral methods in the image domain as well. Spectral methods first say, well, isn't there a way how we can first represent this graph structure in a way which is easily decomposable into graphlets, similarly as how you can decompose an audio signal with things such as a Fourier transformation into a combination of different sinus waves, for instance, different questions here. And the idea is then that we don't stack layers on top of each other, but we try then to do this in a singular layer. A little bit harder to set up, a bit less intuitive, typically also more computationally expensive, so they tend to be utilized less than the spatial methods. Again, I already mentioned this receptive field, but what you can also do as well is it's not so hard to go in there and say, well, this neighborhood function, who is to say that I need to limit myself to the direct neighborhood? I could go friends of friends here as well, and I could consider those nodes to still be in your neighborhood as well. So you could also play with how you define a neighborhood of a node as well, right? Again, less commonly done. The preferred approach is to stack layers, as we saw with CNNs. Also there we said, well, instead of making your filter a 5 by 5, keep it small, but stack more layers. Similar thing here that tends to work better. So again, this is our generic form. So if we have this target node over here, we're updating the representation. It's exactly the same thing. We give its features, the neighbor features, the edge weight. We update that. We aggregate those messages. Combine that aggregation with your own features. Those get updated by this update function. And these Greek letters here, these are just MLPs, basically, that you have. 2 matrix multiplications. And by stacking layers, even for a single node A, you might have widened or looked at a neighborhood that goes further than just B and D in this case. So one well-known implementation for this is the GCN. And then if you look at the formula for this unit, you can start seeing, yeah, this is indeed an instantiation that looks very similar, a little bit differently. What are things that it does? It also considers a node to be part of its own neighborhood. So it's like every node automatically gets a self loop as well. Then you just take the weight between j and I, and you include that there. You need to normalize that a little bit by the degree factor as well. You multiply this with the feature vector that you have for your node j coming out of the previous layer. So in one operation, this becomes this. So this is then basically the implementation that GCN offers, but quite similar to kind of this generic implementation that we just saw. So the question here is, okay, this is it in one operation. If you look here, it doesn't use a gather function as well. It keeps it simpler, and it says, well, just multiply the weight with the features. I don't need an additional MLP inside of here, right? So the only thing I have is this thing, right? And it's here where the weights get learned, basically. So the question here, are the weights part of the message function or the update function? Here they're in the update function because it happens after aggregating the messages, after taking that sum there. Still, drawback here, if you have large networks and nodes have lots of neighbors, and those nodes have lots of neighbors as well, and you stack 5 layers like this on top of each other, effectively, to update a single node, you need to look at the friends of the friends of the friends of the friends of the friends, so you basically spread out. You are already dealing with having to look at a lot of nodes, at large subgraphs, to do this. So even if you could do this update and learn it node by node, even to do it for a single node, the graph that you need to pass in, even if you make that sparse, might still be too large. Then, next step, and this is what GraphSage introduced. GraphSage basically introduced 2 things. One is, again, a different, I will basically show it like this, a different instantiation of this generic GNN idea, but again, it applies message passing. So here it basically uses 2 different weight matrices, and it says, well, what we do is we first multiply your features with a weight matrix where we have weight sharing. So that's just, again, a matrix multiplication or an MLP. We aggregate all of the features of your neighbors, not yourself in this case. We take the mean instead of the sum. Why? Because we like it, right? So that's the aggregation. We multiply that again with W2, so that's there the gathering step that happens. So, okay, that's the instantiation. But on top of that, they also do something else. And they say, this neighborhood function that you have here, don't take all of the nodes in that neighborhood. Every time you're updating, you're learning to change those weights around. Don't work with the full neighborhood, but take a sample. So don't consider messages coming in from all of your neighbors. Take at most 10 of them. And then when you stack layers, you can keep the size of these subgraphs under control. Because if I only use 10 of your neighbors, and then for those neighbors I only pick 4, I can keep my neighborhood more limited. GraphSage introduces this, but then you can say, well, actually, couldn't I also just change this for that previous method that we just saw? Well, sure. And that's also why in something like PyTorch Geometric, they split this up into 2 things. And they say, well, on the one hand, you have the unit defined as this, how it generates its output. And on the other hand, you have this idea of, well, let's call this neighbor sampling. But no matter which unit that you utilize, you can decide to utilize neighbor sampling. So, and if you do not do this and you still use GraphSage, you're just using the definition of the unit itself, then you're not applying neighborhood sampling or neighbor sampling. So the idea of we will take smaller subgraphs is something that you can apply on everything. And then, of course, we live in the era of attention mechanisms. We have already seen, if you look back at the generic definition, the reason why we stick the information of the center node in and combine it with the information of your neighbor node is that, well, depending on what you look like, I might decide to transform this neighbor information differently. If in your feature vector it says age is very high, well, then maybe I know that your friends have a larger impact, and I should maybe keep more information coming in from the xj vectors. Versus maybe if your age is very low, then I know that your friends basically have no impact, and I only retain your vector, but I can throw the incoming information from the friends away. Maybe, right? Something like that. Okay, what you're trying to do is, in fact, you're trying to suggest, well, we are trying to attend, right? Maybe the generic question is, can't we compute hidden states representations for each node, not just by taking then this combination of who are you and who is your friend, but immediately just saying, well, let us give attention scores to all of the neighbors, similarly to what we did previously. And that's then GAT is then a unit that uses an attention strategy. And here the difference that you see is there is this alpha that pops up over here and says, well, at the end, after we have updated the incoming information of xj by, again, doing a weight multiplication here, I'm still going to calculate attention scores for all of these messages. Depending on what I'm looking at, maybe sometimes this message is more important, maybe other times that other message is more important. The attention scores are calculated with this formula, quite similar to what we saw in the generation of an output coming from a transformer model. Well, depending what my input sequence currently looks like, there are parts of that input sequence that play an important role to know what is the next word that I should generate or next token, and there are parts that I can basically bring to zero. Same thing here, if alpha is close to zero, means that this message will be almost blanked out and reduced to zero. It will not play in or pop up in this sum that we are taking then, right? And a message that gets a high attention score, they will show up. So there are many other, that's not the crux here of what I'm trying to tell, because you can already feel, oh wow, 3 units, one after each other. In total, you can easily find 20 of them, right? So they all utilize the similar kind of generic idea of we do message passing, we gather information from these neighbors, we update them in some way. That's the thing that they all share in common. And hence why a library such as PyTorch Geometric, which is one of the most popular ones if you want to do geometric learning, as it's also called, has so many. And then what you do, what it starts to look like is, well, then on your input side, you have your connectivity information, your features of your nodes, your edges, or your graph. You apply a bunch of GNN layers that can deliver you either embeddings for your nodes or embeddings for your edges or embeddings for the graph as a whole. And then the rest of the network is just, yeah, then you produce with that your final output as always, and you design your loss function or you pick your loss function as always. And it all learns like end-to-end again, like we did previously. And then you can say, okay, I have node-level tasks where you focus on things like node classification or node regression. Then you directly take the embeddings that you have created for your nodes. You have edge-level tasks where you want to predict that an edge is going to disappear or an edge is going to appear in the future. And you have graph-level tasks where you basically want to get an outcome, a prediction, which is for the whole graph. Less common, but again, molecules, things like that. Here, this part of inductive versus transductive learning pops back up. In a lot of cases, people go for transductive learning, where you see the same graph in training and testing. But problem, I don't want to have data leakage, but with neural networks, we can apply like a clever strategy to avoid that there is data leakage going on. And the way how we avoid it is, let's say we're doing node-level classification. We're just going to randomly mask out a fraction of our nodes during training. And we ignore these nodes when our network makes predictions and we calculate our loss to update all of those weights with that we have. We ignore the nodes that we have masked out. And then in testing, we see how well that we did on these masked nodes to get some kind of validation error or test error idea. That's okay. And it's not that this makes your setup not generalizable again. If tomorrow there is a new node that shows up, you can also still utilize this network structure, right? This is just a way to kind of perform a validation check, and that's why we randomly censor out some nodes. But it's not fully perfect. And the reason why it's not fully perfect is, yes, you ignore them when you're calculating your loss, but there is another part where you're not ignoring them. And the other part is that in your intermediate setup, you still are generating representations for these masked nodes. And if you apply message passing, or you take, remember, the sum or something like that of all of these messages of I in your neighborhood, or J was it, of node I, and you're doing something with them, you're also looking at the masked nodes in this neighborhood there. Now you might say, isn't that easy to fix? Then just ignore these nodes in the neighborhood, right? And also leave them out in the message passing step. Yeah, but then typically you see that the performance results of your model drops too much. Then why do people do this? Wouldn't it be better to go inductive and say, no, we just make two graphs, one for training and then a completely new version for testing? The reason is that for most publicly available benchmark data sets, there aren't two graphs. And the only way how you could make two graphs is again by cutting in them, but that's what you don't want to do. In practice, however, it is quite common that you are capable to, at two different points in time, construct two different versions of your graph. And then by all means, please go for that setup. Do it inductively rather than transductively. So that's the difference between transductive and inductive learning. That's basically what I just said. Me and a PhD student have published a paper exactly critiquing this, but we're also not the first to do this. Other people have compared inductive and transductive learning and so on, and indeed find that transductive learning has some sort of data leakage because you're not really testing out that there might occur structural connectivity changes in your network over time. You're basically utilizing the exact same connectivity in training and in testing. And if you do it inductively, and maybe today when you're training, you see that on average, everybody has 3 friends, but then a year later, something happens and everybody on average has 10 friends, right? Well, then of course your network will start, your model will start to weaken because it didn't see that during training, but at least then you will know during testing that this might happen. So yeah, a little bit of a drawback, but it's because most of the data sets that people use, they just have the single graph, right? Now, even in the thing that we introduce in our work is we then basically test out the idea of if your graph is sufficiently large enough and you would start cutting in it, would that really be such a horrible thing in terms of your network learning less well and so on? And we do find that there are ways that you can, again, only if you have a single graph, protect yourself a little bit better than what the standard transductive approach does. So think about, again, train test, data leakage is easy to creep in. Yeah, in terms of tooling, you can see some things here. Typically, people need or make a difference between tooling around the data management. So those are the graph databases for storage, for querying. You have tooling for working with graphs in the context as we've been doing it so far. So things like NetworkX. And then you have often tooling specifically then for layout, exploration, and visualization. And those are then tools such as Gephi. NetworkX is very commonly utilized in Python to work with graphs. You also have iGraph. You have this PyTorch geometric thing. You have RustWorkX, which is one written in Rust with bindings to Python. Visual tools, Gephi, horrible tool, but it still contains like most of the functionality and it doesn't crash with medium-sized graphs. You do have Cytoscape, you have JavaScript-based tools. Spark has a GraphX component, which does get utilized in some cases and offers some analytical things as well, but less and less so, to be honest. And then you have your graph databases to store your data, to query data. Neo4j is very popular, memgraph is very popular, EdgeDB, with then very often their own query language, either that being GraphQL or their own query language that they like to utilize. And for deep learning, I've already mentioned PyTorch geometric, but you have a couple of other ones as well. Okay, yeah, GraphX, I'm going a little bit fast over this, but GraphX is basically, yeah, if you think about your Spark instances again and you want to do stuff with graphs, yeah, then it's not just a list of RNNs, then basically you have both vertices, you have both edges, and you need to do something with that. Contrary to other components in Spark, where they have then said, we will step away from this RNN stuff because we have this data frame API. This has not yet fully happened for GraphX yet, which is the reason why not a lot of people like using it, because there you are limited to utilizing this RNN basic API. There exist packages that do implement this, so that's the one that you see here. So they do implement some sort of graph frame, but they have not really been officially taken in yet. This is taking some time, it's going slowly, so yeah, who's to say where that goes to? But certainly possible to also work with graphs in a distributed manner with Spark. Now we take a look at graph database, and that's basically our ending. And graph databases is something that has come outside or from the larger background, let's say, of NoSQL databases. And so we already saw that at some point we had this Hadoop world that was very busy thinking about storing large data volumes and not so being good at querying, or basically telling you, use MapReduce. The database world at that time was good at querying, and they were trying to solve or attack the problem that they had with regards to scaling. So they basically came from the other side, and there people were thinking, yeah, with a database you can kind of vertically scale, you can buy a bigger machine, but horizontal scalability, like where you would just add machines to a network and the thing just works, not so easy for us, because of course we suffer in the relational database management world. A lot of techniques exist there. They scale quite well, but if you really start talking about larger volumes, yeah, you can't easily horizontally scale them, like our friends at Hadoop seem to be quite good at. Why is that? Well, they use a certain underlying relational concept where they link tables together with foreign keys. That's where you get all your data sets from if you ever work in an organization. So you utilize SQL as a query language to work on this, and quite okay. This is a stable language. Always a good tip if you wonder about which programming language to learn SQL. This was also our kind of story when we spoke about Spark. At some point, the reason why we had Hive and Spark SQL is because people wanted support for SQL on top of these technologies as well. So again, they met in the middle at some point. So our DBMSs, they work well, they have good query support, they can scale relatively well. But the reason why they can't scale like something like an HBase or a Hadoop cluster could is because they put a lot of emphasis on consistency. And they follow a so-called ACID model, atomicity, and so on, where they want to keep data consistent at all times, which in the majority of cases, as an organization, is actually something that you want as a property. Now still, let's say that you're like a Facebook or like a Yahoo or like a LiveJournal and so on, and you say, yeah, okay, but we do have a lot of data. These traditional relational databases, they're not doing it for us anymore. So we need something to work better for us. And maybe you are even prepared to give some of that consistency up as well. And then typically then means in this setting, I want to get horizontal scalability, and I can just add new computers and I can just scale out. And no matter if maybe for a certain object in my data storage that I do not always get the latest up-to-date state of information, as long as at some point in time it becomes up-to-date. And the reason is, of course, if you have 100 servers, and it was the same as what we saw with this HDFS thing as well, I can tell one of them, hey, please update the age for customer SEPA, but that server needs to go off and inform the other servers in our network then, and that can take a bit of time. And we will not say, from now on, up until everybody has updated themselves, no one can ask about the age of this customer. So you do lose some consistency there, but you get scalability in return. And people started calling this NoSQL. But it's a bad name because some of these databases that then started to focus on scalability, they still had support for SQL. Very often what people say nowadays is, well, a better name would have been NoRel, because very often they also step away from this relational model that these traditional databases were using, where they said, well, everything needs to be a table, and you need to design the schema for those tables first, and then you link them together, and then you can write your SQL. A lot of these NoSQL databases changed that underlying data paradigm of that data model. And you had very simple ones, of course, because the original idea was we need to go for scalability. So very simple ones were, and this is a story that we already saw, were following exactly the same steps as what the Hadoop world was doing. Like HBase we will only store key value pairs. And then forget about your query language because that's going to be very simple then. Forget about SQL in that case, true. And if you want to write more complicated queries, well, I don't know what you put in your values, could be anything. So here is MapReduce, go ahead and good luck. Later, NoSQL databases, things like MongoDB and so on, they then started to say, well, we are going to impose some structure on these objects that you store. Let's make them JSON objects, for instance. But on the other hand, what we will not do is we don't want to be like the relational databases. You can just immediately start dumping in data. You don't need to first design what your data looks like in those schemas before you can really start putting content in. So we are schema-less, you just dump in objects, and then later, yeah, you can query them in some more fancy ways, or maybe also still with MapReduce, but there is no kind of guarantees in terms of that every element has the same shape and form and so on. And those gave them rise typically to more data lake-oriented approaches, very agile development, quick development, but also sometimes with not the correct quality guarantees down the line. Very often with a focus on being easy to scale horizontally, so distributed by default, and giving up these kind of consistency aspects here as well. Querying facilities all over the place. Sometimes nothing, sometimes their own query language. Now, what came out of here, actually the most interesting result, are those databases that started to appear, which maybe not focused so heavily on, we need to be scalable, but who started to say, well, since we are now rethinking this kind of standard relational model that all of the existing databases are using, rather than thinking we need to be super scalable and so on, can't we think of data modeling paradigms which even go a step further than this relational one, that make the data representation even richer, and maybe where we can also come up with a querying language different from SQL to query that sort of data. And one of the most best known ones out of here did then became the graph database line of technologies. The reason being is that if you think about what a graph looks like, and you want to kind of massage it into this more kind of relational database structure, that you do lose a lot of information. And yes, you can use SQL to query then as if it were a graph, but if you ever need to write a SQL statement that goes something like, give me the list of friends that this user has, and the list of friends becomes a little bit of a recursive mess. It's not always the most SQL to write. And they were looking for something where they said, well, instead of trying to put everything in tables, why don't we, and where you can only link these tables with foreign keys, why don't we just store things as a graph to begin with? Wouldn't that be something that works better? So also important to state is that, yeah, because of these document stores, they go for scalability, but at the cost of consistency, that these first initiatives where people adopted these kind of technologies did not always go well. Not everybody has big data, even if you think you have. So there were some cases where people jumped on these document stores, but where they were then encountering consistency problems down the line. Today, NoSQL is a bit settled. Today we talk about new SQL, because what happened is, of course, the NoSQL world has realized, yes, horizontal scalability is important, but sometimes the fact that you can design some sort of schema is not all too bad. The fact that you can be consistent is maybe also still a good idea. And maybe we should not focus only on scalability. And yes, a querying language is a good idea. And the traditional database world, they have seen, well, actually, you're right, maybe we shouldn't always force users to design a schema first. Or why don't we have support for a data type, a column in a table, where you can just also dump in JSON? And then we also support to query this, or we support to write a MapReduce statement for this as well. So this is what happened. They have grown towards one another. And today you have a couple of cloud companies who are offering like relational databases, but which are very self-monitoring in the sense that they index all over the place. They try to be scalable. They support JSON columns and so on. So these have grown a little bit towards each other. What has remained, of course, from this story is that all these special cases where people said, but let's make it even more rich than the relational model, rather than less rich. Let's focus only on time series. What would a database where everything that you store is a time series look like? What do your aggregations look like? What do your windowing operations look like? Is there something like a probabilistic database and things like that? So likewise, so here you see a couple of examples, like for a time series database, yeah, there you probably want to focus on getting in real-time information. If you're getting in clicks or stock market details or sensor data. If you look at the Internet of Things sector, then these databases have become quite popular. Companies like InfluxDB, TimescaleDB, and some also saying, well, we're going to use SQL as a query language, but we're going to extend it a bit, versus no, we come up with our own query language. Likewise, in the geospatial domain, well, if you only have tables, sometimes instances in those tables, they are properties, and they have geometric objects that are associated to them. It's a logical question if you would say, yeah, but I would like to have a way to easily express in my query language, please give me this property plus every other point on the map that I have stored here, because I've done measurements that are in a radius of 10 kilometers around this property. That should be just as easy to express, give me this column plus 1 from this table, for instance. So also there you have seen that this has become integrated in either specific tools or new tools that were developed, new database technologies that were developed. And then now the databases. So instead of saying I need a table for readers and I need a table for books and a table for genres and then I link them together with foreign keys, why don't I just design it saying I have these node types, I have these edge types, and edges have these features, nodes have these features. And I just store the data directly in the graph structure. So in a way, you could call this your even increasingly modeling in a relational way, rather than trying to model less in a relational way. So the things that you would typically express with many-to-many structures in a relational database, or you would have to start adding in helper tables, like even to implement this friend of thing in a relational database, that means that if users can have multiple friends and the same friend can be the friend of multiple users, that you need to make a new table there, friendship, where you keep user ID 1 and user ID 2 to represent that friendship connection that you have there. So basically you're forging the concept of a relationship, of an interaction, into its own tabular format. Versus here, no, you just have readers as nodes and they can be friend to themselves, right, to other reader nodes. So the typical situation then, this is the many-to-many, you have books, you have authors, a book can have multiple authors, an author can have written multiple books. Yeah, in SQL, that means again that you need there a third table in between that you then call books authors, and you already need to stick in 3 additional lines in your query statement to make sure that these 3 tables link up correctly. Yeah, why? If you think about how a graph schema would look like, now you have books, you have authors, and 2 types of edges. You could do it here with only 1 type of edge, but basically here uses both-way connections there. And then maybe queries would also start looking simpler. Then maybe if you like to know who or which books are written by a particular author, now you say, well, I would like to match a subgraph starting with a book, and then I will follow a written by connection, and then there needs to be an author there, and only those subgraphs where the name of the author, and there is only a single such node, is equal to this person. And then please remove me all the book nodes, or return me all the book nodes, and I'm only interested in their title, so only give me this. So this looks like SQL, but it's not SQL. This is the Cypher query language. And this was introduced by Neo4j. GraphQL is also very popular nowadays as a query language, but a little bit more messy to write, to be honest. You have other graph databases as well that have become quite popular, EdgeDB and memgraph I already mentioned, but you have GraphDB, OrientDB, Allegro Graph, and so on. So both Neo4j and memgraph also support for GraphQL, but we will use Cypher for the assignment at least. So yeah, a graph database then becomes a sort of a hyper-relational database, which does away with the need to join tables all the time together, but immediately express the subgraph that you would like to obtain as part of your query. What does Cypher look like? Again, for the assignment, these slides just show a couple of examples. Read the documentation of either memgraph or Neo4j on Cypher to get some more examples, or ask ChatGPT, which is typically also a good help there to write queries like these, but make sure that you understand or have it explain what it is doing. But every query here starts by saying, what is the subgraph, or subgraphs that you would like to get? And how we are going to express nodes, 2 parentheses, because that looks a little bit like a circle. I only want book nodes. I have a node type book, so I put a colon in there, book after the colon. And later in my query, I want to refer to this node as again. So I'm also going to give it some intermediate name. So okay, for every book node, which I'm going to call B. This would just give me all the book nodes in my database. I don't just want all the book nodes, I want those book nodes together with their written by connections to author nodes. And then again, you can express either directional queries or non-directional queries. And I only want here two written by types of edges. So the basic select query saying give me all of the books then becomes, well, match all the books and return them to me. And likewise, very similar as in SQL, order by limit, those are just taken over, and these work in Cypher as you would expect, more or less as well. Where is also still there, and you can express it in different ways. You can either say, well, give me all the book nodes, but only where the title is equal to beginning Neo4j, or you can stick that with these curly braces directly into the match class as a sort of a shorthand. You pick yourself what you feel is most clean looking, obviously. Join does not exist anymore. Instead, what we do is we just implement that, or we put that directly in the match statement that we have. So here I'm saying, okay, I want a subgraph, give me all the book nodes, and give me their written by connection to author nodes, give me purchased connections to customer nodes, but don't just give me anything or everything rather. Make sure that the author for this node is equal to SEPA, make sure that the customer age is higher than 30, and make sure that the type of this purchase edge was equal to cash. And then give me all the distinct customer names, the unique customer names. So then you start expressing queries which are becoming more complicated, but way easier to express than if you'd have already joined, like here, at least 3, probably 5 tables to each other. So what also is pretty easy once you work with a graph database is that following relationships further than a first order neighborhood is also pretty easy. So here I could say, give me all the books that are coupled to a genre, and genres have subgenres. So one of the subgenres that I want to match is called programming. But yeah, sometimes a book is not just in the programming genre, but a book is assigned to the Java programming genre. And Java programming is itself a subgenre of programming. I want all of them. I want to have the books belonging to programming and also all the subgenres, the subcategories. And that's done by putting this asterisk in between here. And this is saying, well, also include all of the genres where you can find a link between this one and this one, but not just a direct link with the type parent, but basically between 0 to as many steps as you want. So also including the programming genre itself as a genre there, but also the subgenres, the sub-subgenres, the full tree, basically, in this sense. So 0 is the minimum number of connections. You can also provide a maximum number. So you could say, okay, for the user SEPA, I don't want his friends, I want his friends of friends. So only give me those. So then your minimum step would be 2 hops and your maximum step would be 2 hops. Analytics, in the beginning not. Both Neo4j and memgraph said we are an operational database. We are for storing lots of data, querying it as you would use a normal database for. Once you want to start doing some modeling or data science, you basically export your data and you use your favorite Python package to do that. Over time, they have changed their mind, obviously, with this whole AI thing and GNNs coming along. And both Neo4j and memgraph have been adding in add-on libraries where they are now providing support to say, oh, well, a centrality metric like PageRank, I want to calculate that for these nodes in my graph. I want to do community mining, but directly in my database. So they have been implementing a lot of graph algorithms directly in their database layer itself. So which is also pretty nice, means that you do not need to kick out your data from your database to then analyze it. Even in recent years, they have also been implementing GNN-based algorithms for instance, edge prediction. So you can run that on top of these things. It's not going to be probably as performant as if you would completely implement it from scratch with your own architecture that you have designed, but probably it's also a good starting point if you just want to use this as a tool in an organization, but still do something with GNNs. Integration, it's pretty easy to get data out and put it in NetworkX in Python. In Spark, yeah, you can also do that if you use Neo4j, but it's a little bit more messy. There exist connectors between Spark and Neo4j directly. That looks like this. For Aura and Python, like I said, there are libraries that allow you to query your data directly from Python, and then you can dump it in NetworkX to visualize it. For the assignment, it's probably easier if you want to take a subgraph out that you first export it as a CSV file or as a GraphML file or as a JSON file, and then you load that in Python and you visualize it like you want. So that's probably the routes that you would go for, but you can also directly query the graph from Python using something like GQL Alchemy. Visualization, I already mentioned a couple of tools. To be honest, I know that for the assignment, it says that you should utilize Gephi. To be very honest, I don't really care. It's not that I'm such a big fan of Gephi myself. Anything that can allow you to make the point that you want to make, you can utilize. Even if you play around with this style thing in the memgraph query browser and you design everything in there, also fine by me. If you prefer to just make a JSON export or a GraphML export and you load that in Python using NetworkX and you do your visualization in there, also fine by me. Though also in NetworkX, the default visualizations that you get, they look ugly as sin, so you'll also have to change it a bit. So it's not specifically that Gephi contains something special on its own. The only thing that it has is it has a good support for all sorts of filtering mechanisms, metrics that you can calculate, even community mining and so on. But it's in recent years also not very well maintained anymore. It's a bit weird how this is still one of the existing tools that is kind of capable to load in larger graphs as well. I've heard that Cytoscape is also not too bad, but if you would prefer to do it just purely in Python, for me that's also okay. Or purely using Cypher with that query browser, but then you're a bit more limited in terms of styles that you can add in. So in the assignment, Gephi is a good default choice. It's not too hard to learn. The interface is old-fashioned, but to some extent intuitive enough. But if you decide to not use Gephi at all, and you can convince me with a story that looks clean, and you performed a nice analysis, for me that's in fact also okay. But like I said, it does contain a whole bunch of things that are still kind of lacking in other things as well. Like if you do want to calculate betweenness, closeness, centrality, and you want to say, okay, I want to change the size of the nodes based on this, that's very easy to do in something like Gephi. Exporting, yeah, there exist plugins. They don't work that well. So the easier thing is to just say export to GraphML, either by first going through Python or something through R, or using like a shell tool that you have been provided. With Neo4j, that's doable. With memgraph, it's a little bit less mature than that. So that's why you also have gotten a conversion Python script. So where you can first do an export to JSON in memgraph and then convert that to GraphML. And that one is the one that you can easily load into Gephi. So if you want to go the Gephi route, you will probably need that Python script to convert from JSON exports to a GraphML format. And then, yeah, so some use cases, but you will play with that a bit yourself, but as some inspiration, Neo4j itself has a couple of nice example graphs that you can play with across lots of different examples that we have already seen, like a fraud detection, recommendation making on a shopping graph, and so on. These would be easy cases to utilize, but these have already been analyzed by 20,000 Kaggle notebooks, so not so much fun things to find in there anymore. They also have a sandbox where you can play with like Russian Twitter troll data sets and the Paradise papers and so on. So that's the one that we utilized years ago, is an analysis of these Panama papers in this course. Year later, we looked at the mandates of politicians, and then what you find is, yeah, there are obviously two communities here, and you might expect in Belgium that the two communities are according to left-wing versus right-wing party, but not the case for mandates. It's of course which language that the political party speaks. This was a use case with Twitter bots, scraped a bit more recently than the one that Neo4j puts out. So an enormous graph of posts, users following each other, posting, and so on. The year after that, we did it with Reddit posts using the COVID subreddits, so that was also fun. And then we scraped a whole bunch of YouTube movies to see if there is kind of bias in the YouTube recommendation system. Then we utilized TikTok videos, so also a large graph. Then we looked at Twitch streamers. Then we looked at politicians on X again. So yeah, after a while, you start running out of social networks to utilize. So this year, it's Steam information. And it's games on Steam and purchase information, friend information. Not sure what you can do with that, but try to make something focused, maybe focus on a specific game or focus on a specific tag. I like to show these graphs on these slides, but obviously do take away that this is something that, oh, wow, looks cool, but says nothing, right? I mean, if you really want to tell a story, you will need to zoom in on smaller graphs to get that out of there, or smaller patterns to get that out of there. Good. I have 8 minutes to tell you a bit about the exam, right? Which is more than plenty. So the exam, it consists out of 2 parts, multiple choice question part with guess correction being applied. That's about 15 to 20 multiple choice questions, typically not hard at all. If you have been following along with the assignments, very often that multiple choice part is a breeze. On top of that, there is also 1 or 2 open questions, which typically is more of the style, calculate something or use a bit of creativity, like how would you approach this problem using the tools that we have seen. The focus is not to memorize formulas. So retain insights, think about general workings, pros and cons. Do not focus or memorize all of the formulas that we have seen. If you need them, I will provide them to you. Now, there is one exception. Every time I ask some students to draw an ROC curve, they will tell me, yeah, but you told us that we shouldn't memorize formulas. I mean, true positive rate, false positive rate, the name itself hopefully will tell you what that is, right? So how you calculate recall or precision, that's the bare bones, right? But what I'm saying is like a GNN unit, what does it look like for GCN? Please reproduce this. No, that's not the idea, right? So example question, and the background material, of course, is extra, so you don't need to, that's not part of the study material. Common or questions from the past. Why is a random forest called random? Isn't that weird? What makes a random forest random? 2 reasons, right? Because there is this bootstrapping on the one hand, and the fact that it applies a random selected subset of features in every split of every tree. That's what makes it random. Why is then an isolation forest called an isolation forest? Here are 10 instances with predictions. Draw an ROC curve for them, something like that. Explain with permutation-based feature importance. Explain with a small example how that works, right? Which pre-processing steps are necessary when you use L2 regression? 4 options for the multiple choice questions. One of them does not apply, and maybe that one not, or maybe that one yes, which is correct, which is incorrect. Examples of things which will not be asked is write down the full cross-entropy loss function, or write down this GCN unit for the GAT GNN unit. Sadly not, although it's a nice question, is please prove why a single hidden layer is enough to construct a universal approximator. You need to know that it is enough to have a universal approximator, but you will not be asked to prove that. Don't write down the history of Hadoop. I mean, this is just fun to know, but it's not a history course. I mean, so use your common knowledge. I don't think I make it too crazy. Or don't write down the full AdaBoost algorithm. But rather than this, I explain a bit what's the idea behind AdaBoost, for instance, and what does the boost in AdaBoost refer to, and what makes it different from bagging, right? So more in those general terms that you know the jargon a bit, not full reproduction of formulas. That's not the idea. If I want formulas, I can ask ChatGPT, basically, right? Which is actually a good remark, I think. I think the style of questions are more in the way of the next time that you chat with ChatGPT, would you at least be able to tell, hey, you're hallucinating now, and maybe there you're not fully correct, right? I think that should be more the goal of how we try to evaluate these things more and more. Also, yeah, there is always more. So try to continue learning if you were interested in this, following news sources and keeping up with coding and playing around with stuff. Be curious, explorative, creative, play around with things that you see and keep thinking. And yeah, other than that, thanks for being part of this semester. I hope that you had fun as well. And good luck with finalizing the assignments. If you do have questions about that, you can also still always email me, by the way, so don't hesitate to do that. Keep an eye out for the deadline of assignment 1. Other than that, see you at the exams, and good luck with that.